Hello there, and welcome to Science for Sleep, where curiosity gets cozy, and even the biggest questions in the universe are allowed to unfold at a slow, unhurried pace. Tonight's gentle journey is one that stretches far beyond anything we usually think about, something so vast that even the word distance begins to feel a little inadequate. Because instead of asking how far something is, we're going to ask something slightly different and perhaps a bit more intriguing. How long would it really take to cross the universe? It sounds like a simple question at first, doesn't it? Almost like asking how long it takes to drive across a country, or maybe how long a flight might be if you're heading somewhere distant and exciting. But the moment you try to apply that same kind of thinking to the universe, things begin to shift. The numbers grow larger, the familiar landmarks disappear, and suddenly the idea of getting from one side to the other becomes something far less straightforward. Because the universe isn't just big, it's, well, we'll take our time getting there. Before we wander too far into the vastness, let me ask you something simple. Where are you listening from right now? And perhaps just as fitting for tonight's topic, what time is it where you are? It's a small question, but there's something quietly interesting about it. Each of us, in different places around the world, is experiencing this moment from our own little corner of space. Different clocks, different surroundings, and yet here we are, all arriving at the same idea together, thinking about distance, thinking about time, and how the two are more connected than they might first appear. If you find this kind of slow exploration calming, or if it helps your thoughts settle just a little after a long day, feel free to give the video a like, or maybe subscribe. It helps this quiet space reach others who might be looking for the same kind of gentle pause. Now, as we ease into the question itself, it helps to start somewhere familiar. Not the whole universe just yet. That would be a bit like trying to read the last page of a book before you know any of the characters. Instead, we'll begin with something closer. Something we can almost picture without too much effort. Imagine standing outside on a clear night, looking up at the sky. You might see a few stars, maybe a faint band of light stretching across the darkness if you're somewhere with a little light pollution. That soft hazy streak is part of our home galaxy, the Milky Way. And even though it looks calm and still, it's anything but small. But even that is getting ahead of ourselves. Let's shrink things down for a moment. Not the universe, just our starting point within it. Right now you're on Earth, a planet that feels quite large when you're standing on it, but in cosmic terms it's actually quite modest. If you could somehow step back and look at the entire planet from a distance, it would fit comfortably inside your field of view. And if you kept stepping back farther and farther, Earth would quickly become just a tiny dot. And yet, even crossing Earth takes time. A long flight across the planet can take many hours. Walking it would take months, maybe years, depending on how determined you are and how often you stop for snacks. So already, even at this small scale, distance and time are closely linked. But here's where things begin to stretch. If you travel from Earth to the Moon, which is our closest cosmic neighbour, the distance is about 384,000 kilometres. That sounds like a lot, but in space terms it's actually quite close. Astronauts have made that journey in just a few days. Now imagine continuing outward, past the Moon, toward the Sun. The distance increases dramatically. The Sun is about 150 million kilometres away from Earth. If you were travelling in a typical passenger plane, it would take well over a decade to get there. Not exactly a convenient commute. And yet, even the distance to the Sun is still considered nearby when we start thinking about the universe as a whole. Because the moment we step outside our solar system, the scale changes again. The nearest star beyond our Sun is Proxima Centauri. It's about 4.24 light-years away, and that's where things get interesting, because instead of measuring distance in kilometres or miles, we start using something else entirely. Light-years. A light-year is the distance that light travels in 1 year. And light, as it turns out, is incredibly fast. It moves at about 300,000 kilometres per second. That's fast enough to circle the Earth more than 7 times in a single second. So when we say that something is 4 light years away, what we're really saying is that even light, moving at the fastest speed possible in the universe, takes over 4 years to get there. Now, just let that settle for a moment. Even at the absolute speed limit of reality, the closest star is still years away, and we haven't even left our local neighbourhood yet. This is where the question we started with begins to take on a slightly different shape. Because when we ask how long it would take to cross the universe, we're not just asking about distance, we're also asking about speed, about limits, about what's actually possible. If you were walking, the journey would be, well, we'll come back to that later. It's a surprisingly entertaining thought experiment. If you were flying in a plane, things would be faster, but not by nearly enough. Even our fastest spacecraft, which can travel at tens of thousands of kilometers per hour, would take tens of thousands of years just to reach the nearest star. So already, before we've even begun to think about the entire universe, we're facing a quiet realization. Space is not just big, it's big in a way that resists intuition. And yet, we still try to measure it, to understand it, to imagine crossing it. There's something very human about that. The desire to take something vast and turn it into a journey. To ask, how long would it take? As if the universe were a road we could simply follow. But the universe doesn't quite behave like a road. For one thing, it doesn't have clear edges in the way we might expect. When we talk about crossing the universe, we usually mean the observable universe, the part we can actually see, and even that has a size that's difficult to fully grasp. The observable universe is about 93 billion light-years across. That number might sound familiar in structure, but the scale it represents is, well, we'll take our time with that in the next part because it deserves a careful introduction rather than being rushed past like a roadside sign. For now, it's enough to notice something simple. Even if you could travel at the speed of light, crossing the observable universe would take tens of billions of years. And that's under the most optimistic assumption possible, because there's a small complication we haven't talked about yet. The universe is expanding, which means that while you're travelling, the distance you're trying to cross is actually getting larger. It's a bit like trying to walk across a moving walkway that's going in the opposite direction. You're making progress, but the destination keeps drifting away, and that raises an interesting question. If the universe keeps expanding, can you ever truly cross it at all? We'll come back to that. Gently. For now, let's stay with the feeling of scale, the sense that the universe isn't just large but layered, that every time we zoom out, what once seemed enormous becomes just another small step in a much bigger picture. From Earth to the moon, from the moon to the sun, from the sun to the nearest stars. Each step feels like it should be enough, like we've already gone far beyond what we can easily imagine. And yet, each time there's more. So instead of jumping straight to the edge of the universe, it might be more helpful to build our way there slowly, to understand what crossing the universe actually means, one piece at a time. Because once we start to see how these distances connect, how they build on each other, the question becomes less about a single journey and more about a series of them. A journey across the solar system, a journey across the galaxy, a journey between galaxies, and only then, eventually, a journey across everything we can see, each one with its own sense of scale, its own sense of time. Trying to picture the size of the universe is a bit like trying to picture the number of grains of sand on every beach at once. You can start the thought, you can even get a rough sense of it, but at some point your mind gently taps out and says, that's probably enough for now, and that's perfectly alright, because when we talk about how big the universe is, we're not really aiming to hold the entire thing in our heads at once. Instead, we're going to do something much more manageable. We'll build up to it slowly, step by step, the same way you might zoom out on a map starting with your street, then your city, then your country, until eventually you're looking at the whole planet, only this time the map keeps going. Let's begin somewhere familiar again, just to keep things grounded. Imagine Earth as a sphere about the size you're used to seeing on a globe. If you were to travel all the way around it at the equator, you'd cover roughly 40,000 kilometers. That's already a significant journey, long enough to require careful planning, snacks, and perhaps a few breaks along the way. Now, take that entire planet and place it next to the Sun. The Sun is so large that you could fit about 1.3 million Earths inside it. Not lined up neatly, but packed together like tiny marbles inside a glowing sphere. If Earth were the size of a small bead, the Sun would be more like a large exercise ball. And yet, even with that comparison, we're still only dealing with one star. Around the Sun, there are planets, moons, asteroids, and distant icy objects, all forming what we call the solar system. The distance from Earth to the Sun, as we mentioned earlier, is about 150 million kilometers. Astronomers call this one astronomical unit, or AU, a kind of convenient measuring stick for distances within our solar system. But the solar system doesn't stop at Neptune, the outermost planet. Beyond that lies a region called the Kuiper Belt, filled with icy remnants from the early days of planetary formation. And even beyond that, stretching far into the darkness, is something called the Oort cloud. The Oort cloud is less like a belt and more like a vast spherical shell of icy objects surrounding the Sun at extreme distances. If the Earth-Sun distance is 1 unit, the Oort cloud extends tens of thousands of times farther out. If you were to travel from the Sun to the outer edge of the Oort cloud at the speed of light, it could take more than a year. And that's still just our solar system. Already the scale has grown from something we can easily relate to, like flying across Earth, to something that takes light itself a year to cross. But even this is still considered local in the grand scheme of things. Now let's take another step outward. The nearest star system, Proxima Centauri, sits about 4.24 light-years away. That means the light we see from it tonight actually left that star over 4 years ago. It's a small delay on human timescales, but it's enough to remind us that space isn't just large, it's layered with time. Between stars there is mostly emptiness. Not complete nothingness, but something very close to it. A few stray atoms, occasional particles, and long stretches where there's simply not much going on. If you were travelling between stars, most of your journey would be spent moving through this quiet, nearly empty space. But stars are only the beginning. They gather together into something larger, something structured, something with a shape you might even recognise if you've seen images of it before. Galaxies. Our own galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. It's a vast rotating disk of stars, gas and dust, with spiral arms that stretch outward like the gentle curve of a pinwheel. If you could look at it from above, it would appear as a luminous swirl bright in the centre and fading toward the edges. But from where we are inside it, we don't see the full structure. We see it as a band of light across the sky, a soft glow made from countless distant stars. Now, here's where the scale takes another leap. The Milky Way is about 100,000 light-years across. That means if you could travel at the speed of light, the absolute fastest speed possible, it would still take 100,000 years to cross from one side of our galaxy to the other. Not days, not centuries, 100,000 years. And remember, that's at light speed. If you were travelling at the speed of one of our current spacecraft, the journey would take millions of years. So already, just crossing our own galaxy becomes something that stretches far beyond a single lifetime, or even many lifetimes. But as before, the Milky Way is not the end of the map. It's just one galaxy among many. Nearby there's the Andromeda Galaxy, our closest large galactic neighbour. It sits about 2.5 million light-years away. The light we see from Andromeda tonight began its journey before humans even existed in their current form. Between the Milky Way and Andromeda, there is an enormous expanse of space, mostly empty, with only a few scattered particles drifting through it. And beyond these two galaxies there are others, thousands, millions, billions. Galaxies themselves form groups, clusters, and even larger structures called superclusters. These are like cosmic cities, where galaxies gather together under the influence of gravity. Our galaxy is part of the local group, a small collection of galaxies bound together. The local group itself is part of a larger structure known as the Virgo supercluster. And even that is part of something bigger still, a vast network of galaxies stretching across space like threads in a cosmic web. If you could zoom out far enough, the universe would start to look less like a collection of isolated objects and more like a kind of structure with filaments, clusters, and enormous voids in between. And those voids are truly vast. There are regions of space where there are very few galaxies at all, enormous stretches where you could travel for millions of light years without encountering much of anything. So when we talk about crossing the universe, we're not just talking about moving through a dense field of stars. We're talking about navigating a landscape that alternates between crowded clusters and immense emptiness. Now let's bring all of this together. The observable universe, the part of the universe we can actually see, has a diameter of about 93 billion light years. That number might seem surprising at first. After all, the universe is about 13.8 billion years old, so you might expect the observable universe to be about 27.6 billion light years across, accounting for light travelling in both directions. But because the universe has been expanding during that time, the objects we see today are much farther away now than when their light began its journey. So the observable universe ends up being far larger than a simple multiplication might suggest. And within that observable universe, there are an estimated 2 trillion galaxies, each one containing billions or even hundreds of billions of stars, each star potentially surrounded by planets, each planet a possible stage for its own story. Now, as these numbers grow, something interesting happens. They start to lose their sharp edges. A million feels similar to a billion. A billion feels similar to a trillion. The differences are enormous, but our intuition doesn't quite keep up. So instead of trying to hold all of it at once, it can help to think of it as layers. Earth, a small planet. The solar system, a neighborhood. The Milky Way, a city of stars. Clusters and superclusters. Entire regions of that city. And the observable universe, everything we can currently see, each layer larger than the last, each one stretching the idea of distance a little further. And yet, even with all of this, there's something important to remember. The observable universe is not necessarily the entire universe, it's just the part from which light has had time to reach us since the beginning. There could be more beyond it, much more. Possibly even infinitely more, but we can't see it, at least not yet. So when we ask how long it would take to cross the universe, we're usually talking about crossing the observable universe, because that's the part we can actually define. And even that, as we've seen, is vast beyond anything we encounter in everyday life. If the universe is this large, what is the fastest way to move through it? And more importantly, is there a limit to how fast anything can go? At this point, with distances stretching into thousands, millions, and billions of light years, it's natural for the mind to reach for a simple solution. If everything is that far apart, then surely the answer is just to go faster. After all, that's how we solve distance here on Earth. If a place is far away, we don't question whether we can reach it, we just look for a faster way to get there. Walking becomes driving, driving becomes flying. Flying becomes something even quicker if we can manage it. Speed feels like the obvious answer. So it's tempting to imagine that if we could just keep increasing our speed, pushing a little further each time, we might eventually reach a point where crossing even the universe becomes manageable. Maybe not easy, but at least possible within a reasonable stretch of time. But this is where the universe gently interrupts that line of thinking. Because unlike roads, oceans, or even the empty space between planets, the universe has a built-in limit, a speed that cannot be exceeded, no matter how advanced your technology becomes, no matter how much energy you're willing to use, no matter how determined you are. That speed is the speed of light. Light travels at about 299,792 kilometers per second. It's such a precise number that scientists have actually defined it exactly and built their entire system of measuring distance around it, not the other way around. To give that a bit of perspective, in 1 second, light could circle the Earth more than 7 times. It could travel from Earth to the Moon in just over a second. From the Sun to Earth in about 8 minutes. It's fast in a way that doesn't really have an everyday comparison. And yet, as fast as it is, it's not just very fast. It's something more fundamental than that. It's woven into the structure of reality itself. Now, you might wonder, why that speed? Why not faster? Why not something else entirely? That's one of those questions where physics gives us a clear rule, even if the deeper why still feels a bit mysterious. What we do know is that this speed isn't just about light. It's about how information, energy, and cause and effect move through the universe. Nothing with mass can reach or exceed this speed. Not rockets, not particles, not even the most advanced spacecraft you can imagine. And the reason for that has to do with how motion, energy, and time are connected. Let's take a simple idea first. When you push something to make it move, you're giving it energy. The faster you want it to go, the more energy you need to supply. That's intuitive enough. Pushing a bicycle to go faster takes more effort than letting it roll gently. But as objects move faster and faster, something subtle begins to happen. Their resistance to acceleration increases. In everyday life, we call this inertia. It's why a heavier object is harder to push than a lighter one. But at very high speeds, especially speeds approaching the speed of light, this effect becomes much more pronounced. It's as if the object begins to behave as though it's gaining more and more mass, even though nothing is being added to it. So to keep accelerating it, you need more and more energy. And not just a little more, exponentially more. The closer you get to the speed of light, the more extreme this effect becomes. Each small increase in speed requires a disproportionately large increase in energy, until eventually, as you approach the speed of light, the amount of energy required becomes effectively infinite, which means that no matter how powerful your engines are, no matter how advanced your technology becomes, you can never quite reach that final step. You can get closer and closer, but you can't cross it. It's a bit like trying to reach the horizon. No matter how far you travel, it always remains just out of reach. Now, this might seem like a limitation, and in many ways it is. It sets a hard boundary on how quickly we can move through space, but it also keeps the universe consistent, because this speed limit isn't just about motion, it's also about time. To see how those two are connected, imagine 2 observers. One is standing still, and the other is moving very, very fast. According to classical thinking, both of them should agree on how time passes. A second is a second, no matter what. But that's not what actually happens. As objects move faster, time for them begins to slow down relative to someone who is stationary. This effect is called time dilation, and it's not just theoretical. It's been measured in experiments with incredibly precise clocks. Clocks moving at high speeds tick slightly slower than those at rest. The difference is tiny at everyday speed, so you don't notice it when you're in a car or on a plane. But as you approach the speed of light, the effect becomes more and more significant. From the perspective of someone travelling at near light speed, time itself stretches. A journey that might take years for someone watching from Earth could feel much shorter for the traveller, and this is where things start to become quietly fascinating. Because while the speed of light limits how fast you can move through space, it doesn't limit how you experience time during that journey. In other words, you might not be able to reach distant parts of the universe quickly from an outside perspective, but from your own perspective, the trip could feel much shorter. We'll explore that idea more carefully later, because it has some surprising implications. For now, it's enough to notice that speed and time are not independent. They're deeply connected, and the speed of light sits right at the centre of that connection. Another way to think about this limit is through information. Imagine you turn on a light in a distant room. The moment you flip the switch, the light doesn't appear everywhere instantly. It spreads outward at the speed of light. This means that there is always a slight delay between an event happening and that information reaching somewhere else. Even when you look at the sun, you're seeing it as it was 8 minutes ago. If the sun were to suddenly disappear, we wouldn't know immediately. We would continue to see it shining for 8 more minutes, because that's how long its light takes to reach us. This delay isn't a flaw, it's a fundamental feature of how the universe works. Cause and effect depend on it. If information could travel faster than light, things would become complicated. Events could appear to happen before their causes. The order of events could become inconsistent depending on how you were moving. The universe, in a sense, would lose its sense of sequence. So the speed of light doesn't just limit motion, it preserves the structure of reality. It keeps events in a consistent order, ensuring that causes come before effects. And that's quietly important. Because when we ask how long it would take to cross the universe, we're not just asking about distance and speed. We're also asking about the rules that govern how those two interact. And one of those rules is clear. No matter what you build, no matter how advanced your civilization becomes, you cannot outrun light. You can approach it. You can get very close, but you can never exceed it. Now, there are a few interesting exceptions that sometimes come up in discussions. For example, space itself can expand faster than light. Distant galaxies can move away from us at speeds greater than the speed of light, not because they're travelling through space that fast, but because the space between us and them is stretching. But that's a different kind of motion. It doesn't allow you to send a message faster than light, or travel faster than light in the usual sense. It's more like the distance itself is changing rather than anything moving through it. There are also theoretical ideas, things like warp drives or wormholes, which suggest ways of getting around this limit by bending space instead of moving through it. But those remain, at least for now, firmly in the realm of theory. They require conditions and forms of energy that we don't currently know how to create or control. So for the purposes of our journey, it's best to work with the rule as we understand it. The speed of light is the ultimate speed limit, and that has a direct consequence for our original question. If you want to cross the universe, the fastest possible way to do it is at the speed of light, which means that the minimum time required is measured in light years, billions of them. And that's assuming the universe isn't expanding, which, as we've already noted, it is. So even under the most optimistic conditions, crossing the universe is not just a long journey. It's a journey defined by the very structure of reality. Now that we've settled, gently and without too much urgency, on the idea that light represents the ultimate speed limit, it becomes something more than just a physical phenomenon. It becomes a kind of traveller. Not one that chooses where to go or decides when to stop, but one that moves steadily, reliably, carrying information across the vastness of space. And because nothing can go faster, light gives us a natural way to measure distance in terms of time. Instead of asking, how far away is something, we begin to ask, how long does light take to get there? It's a small shift in wording, but it changes the way we think about space quite significantly. Distance becomes duration. Space becomes something you move through not just with speed, but with patience. So let's follow light for a while. Not all the way across the universe just yet, but step by step, as it moves through the different layers we've already started to explore. We'll begin, once again, close to home. If a beam of light leaves the surface of the Earth and travels to the Moon, it takes just over 1 second to arrive. About 1.3 seconds to be a little more precise. That means when astronauts stood on the Moon and spoke to people back on Earth, there was always a small delay. Not because of faulty equipment, but because even light needs a moment to cross that distance. It's brief enough that we don't usually think about it, but it's there. Now if we send that same beam of light toward the Sun, the journey becomes noticeably longer. Light takes about 8 minutes to travel from the Sun to Earth. So when you look at sunlight, when you feel its warmth, you're experiencing something that began 8 minutes ago. It's a quiet reminder that even the most familiar things we see are slightly delayed versions of reality. If the Sun were to change suddenly, we wouldn't know immediately. The light carrying that information would still need those 8 minutes to reach us. And already, with just these two examples, something begins to settle into place. Light is fast, incredibly fast, but space is still large enough to make even that speed feel measurable. Let's keep going. If light travels from the Sun to Neptune, the outermost planet in our solar system, the journey takes about 4 hours. That's still within a single afternoon if you imagine it that way. But if we extend that journey to the outer edges of the solar system, toward the distant Oort cloud, the time stretches much further. Depending on how far out you go, light could take more than a year to reach the farthest reaches of our solar system. So even within what we call our local neighbourhood, light itself needs a year to cross it. And yet, this is still just the beginning. Now let's follow light beyond the solar system, into the space between stars. As we mentioned earlier, the nearest star, Proxima Centauri, is about 4.24 light-years away. That means the light we see from it tonight began its journey over 4 years ago. If you were to imagine light as a traveller leaving that star, it would have been on its way toward Earth for years before arriving at your eyes at this very moment. And between stars, the distances grow quickly. Within our galaxy, stars are separated by several light-years on average. Some are closer, some are farther, but the pattern remains the same. Light travels for years, sometimes decades, sometimes centuries, just to move from one part of the galaxy to another, and then we reach the scale of the Milky Way itself. As we've already seen, the galaxy is about 100,000 light-years across. So if light were to start at one edge and travel straight through to the other, it would take 100,000 years to complete that journey. Not because light is slow, but because the galaxy is vast, and that number, 100,000 years, begins to shift how we think about time as well. It's far longer than recorded human history, longer than civilizations, longer than languages, longer than almost anything we commonly measure. If light began crossing the Milky Way when early humans were just beginning to use simple tools, it would still be travelling today. Now let's step outside the galaxy. If light leaves the Milky Way and heads toward the Andromeda Galaxy, the journey takes about 2.5 million years. That means the light we see from Andromeda tonight began its journey long before humans existed in their current form. It left when the Earth was a very different place. So when we look at distant galaxies, we're not just seeing faraway objects, we're seeing into the past. Light becomes a kind of messenger, carrying images of what the universe looked like millions or even billions of years ago. And as we move farther out, this effect becomes even more pronounced. There are galaxies so distant that their light has been travelling for over 10 billion years before reaching us. By the time that light arrives, the galaxies themselves may have changed, merged, or evolved into something entirely different. So in a very real sense, the universe we see is not the universe as it is now, but the universe as it was when that light began its journey. Light doesn't just tell us where things are, it tells us when they were. Now let's take one more step outward, toward the largest scale we can observe. At the very edge of the observable universe, we detect something called the cosmic microwave background. It's the oldest light we can see, a faint glow left over from when the universe was very young. This light has been travelling for about 13.8 billion years. It began its journey shortly after the universe itself came into existence, and it's only now reaching us. So if we imagine light as a traveller again, this particular journey has lasted almost the entire lifetime of the universe. And yet, because of the expansion of space, the source of that light is now much farther away than 13.8 billion light-years. In fact, it's part of what gives the observable universe its current size, about 93 billion light-years across. So here's where everything begins to come together. Light gives us a way to measure space in terms of time. It shows us that even at the fastest possible speed, crossing the structures of the universe takes enormous durations. Seconds to reach the moon, minutes to reach the sun, hours to cross the inner solar system, years to reach the outer edges, years again, but multiplied many times, to reach nearby stars. Hundreds of thousands of years to cross a galaxy. Millions of years to move between galaxies. Billions of years to reach the farthest edges of what we can see. and all of this is just for light. If we were to imagine ourselves as travellers instead, moving at slower speeds, these durations would stretch even further. But even before we think about that, there's something quietly important to notice. Light never stops. It doesn't tire, it doesn't slow down, it doesn't take breaks. Once it begins its journey, it continues second after second, year after year, crossing vast distances without interruption. And yet, despite that steady motion, the universe is large enough that even light takes immense amounts of time to move through it. So when we ask how long it would take to cross the universe, light gives us a kind of baseline, a best-case scenario. It tells us the minimum possible time required, assuming you could travel at the fastest speed allowed by reality, and even then the journey spans billions of years. But there's another detail that makes things even more interesting. From the perspective of light itself, no time passes at all. Now, that might sound a little strange at first, but it comes from the way time behaves at extreme speeds. At the speed of light, time effectively stops. For light, the moment it is emitted and the moment it's absorbed are the same. It doesn't experience the journey the way we would. So while from our perspective, light may take billions of years to cross the universe, from its own perspective, the trip is instantaneous. It's as if distance collapses completely. And that contrast between what we observe and what is experienced hints at something deeper about the relationship between space, time, and motion. Because as we move closer to the speed of light, our own experience of time begins to change as well. If you were to begin a journey outward from Earth, not in a rush, but with the quiet intention of simply continuing forward, one steady direction into space, you would quickly notice something curious. The distances begin to grow, yes, but not all at once. At first, things still feel reachable. The moon is close enough to imagine, the sun distant but familiar. Even the planets, though far, still feel like neighbours in a shared space. This region, everything gravitationally bound to our sun, is what we call the solar system. And if we want to understand how long it might take to cross the universe, it helps to begin here, because this is the only part of space where human travel is actually taking place. Now, compared to galaxies or the observable universe, the solar system is quite small, but that doesn't mean it's small in any everyday sense. In fact, it's so large that even the fastest machines we've ever built take years just to move through a fraction of it. So rather than thinking of it as a compact cluster of planets circling neatly around the sun, it's more helpful to imagine it as a vast, layered region, where most of the space is empty, and the interesting objects are scattered like distant islands. Let's start from where you are right now. Earth orbits the sun at a distance of about 150 million kilometres. That's our baseline, one astronomical unit. From here, the nearest destination is the moon, and as we mentioned earlier, even light takes over a second to get there. Human missions have made that journey in a few days, which, in cosmic terms, is impressively quick. But if you were to continue outward, the next major destination is Mars. At its closest, Mars is about 54 million kilometres from Earth, though that distance changes depending on where the two planets are in their orbits. When spacecraft travel to Mars, the journey typically takes around 6 to 9 months, and that's with carefully calculated trajectories, using gravity and momentum in very precise ways. Already you can begin to see the pattern. Even within our own solar system, travel is not instantaneous. It requires time, planning, and patience. Moving farther out, we reach Jupiter, the largest planet in the solar system. It sits about 5 times farther from the Sun than Earth does. Spacecraft travelling to Jupiter can take several years to arrive, often using gravity assist from other planets to build up enough speed. Saturn lies beyond Jupiter, and reaching it can take even longer, sometimes close to a decade depending on the mission design. And then there are Uranus and Neptune, the distant ice giants. Neptune, the farthest planet from the Sun, is about 30 astronomical units away. That means it's 30 times farther from the Sun than Earth is. The only spacecraft to visit Neptune so far, Voyager 2, took about 12 years to reach it. 12 years, just to reach the outer edge of the planets. Now, at this point, it might feel like we've reached the boundary of the solar system. After all, Neptune is the last of the major planets, and beyond it, there are no more large, familiar worlds. But the solar system doesn't end there. Beyond Neptune lies the Kuiper Belt, a region filled with icy bodies, remnants from the early formation of the solar system. Pluto, once considered the 9th planet, resides here, along with countless smaller objects. The Kuiper Belt extends out to about 50 astronomical units from the Sun. Voyager 1 and Voyager 2, those same spacecraft launched in the 1970s, are currently travelling through this region and beyond. They've been moving for decades, and they're still within the broader influence of the Sun. That alone gives a sense of scale. These spacecraft have been travelling for over 40 years, and they haven't even fully left the solar system. Because beyond the Kuiper Belt lies something even larger, the Oort cloud. This is not a dense region like the asteroid belt or the Kuiper Belt. It's more like a vast spherical halo surrounding the Sun, extending tens of thousands, possibly up to 100,000 astronomical units away. To put that into perspective, if Earth were 1 unit from the Sun, the outer edge of the Oort cloud could be 100,000 times farther out. If light were to travel from the Sun to the outer edge of the Oort cloud, it could take over a year, possibly even longer, depending on how far the cloud extends. And remember, light is moving at the fastest speed possible, so crossing the solar system, from the inner planets all the way to the distant reaches of the Oort cloud, is not a short trip. At the speed of light, it takes more than a year. At the speed of our fastest spacecraft, it would take tens of thousands of years. And at human walking speed, well, that's a thought experiment we might gently set aside for now, simply to keep things manageable. What's important here is not the exact numbers, but the pattern they reveal. Even within our own solar system, distances quickly exceed anything we encounter in everyday life. Planets are not close neighbours in the way cities are. They are separated by millions, sometimes billions of kilometres of empty space, and most of the solar system is just that, empty. If you were travelling through it, you would spend most of your time moving through vast stretches of nothing, with only occasional encounters with planets, moons or other objects. It's less like travelling through a crowded place, and more like crossing an ocean where the islands are few and far between. Now, let's consider what it means to cross the solar system. If we define the solar system as extending out to the Oort cloud, then crossing it means starting near the Sun and travelling outward until you reach that distant boundary. At light speed, that journey takes over a year. At current spacecraft speeds, tens of thousands of years, and already we can see something important. If it takes that long just to cross our own solar system, then crossing larger structures, like galaxies or the observable universe, will take proportionally longer. But there's another detail worth noticing. The solar system is not static. Everything within it is in motion. Planets orbit the Sun. The Sun itself moves through the galaxy. Even the Oort cloud is influenced by gravitational interactions with passing stars. So if you were to attempt to cross the solar system, you wouldn't be moving through a fixed environment. You'd be moving through something that is constantly shifting, slowly but steadily. This adds another layer to the idea of travel, because it's not just about distance and speed, it's also about timing, about trajectories, about where things will be, not just where they are. And that's something spacecraft engineers already have to consider. When we send missions to other planets, we don't aim for where the planet is at launch. We aim for where it will be when the spacecraft arrives. In a sense, even within our own solar system, travel is a kind of prediction. Now, as we step back from these details, the solar system begins to take on a different character. It's no longer just a collection of planets. It's a vast region of space, defined by the gravitational influence of the Sun, stretching far beyond the familiar orbits we learn about early on. And crossing it is not trivial. It's a journey that, even at the fastest speeds we can achieve today, would outlast entire civilizations. But in the context of the universe as a whole, the solar system is still just a small neighbourhood, a starting point. If crossing the solar system already stretches our sense of time and distance, what happens when we try to cross something much larger? Leaving the solar system behind, even just in thought, changes the scale of everything in a very noticeable way. What once felt vast begins to shrink into something more manageable, almost like stepping away from a city and realizing it's just one small cluster within a much larger landscape. Out here, beyond the distant edge of the Oort cloud, the sun is no longer the center of attention. It becomes just another star, one of many, quietly moving through a much larger structure. That structure is the Milky Way. From the inside, it doesn't look like much more than a soft band of light stretching across the night sky, a kind of hazy glow made from countless distant stars blending together. But that gentle appearance hides something much larger. The Milky Way is enormous, not in a way that can be easily compared to anything on Earth, but in a way that becomes clearer if we take it one step at a time, just as we've been doing. Imagine for a moment that you could place the entire solar system into a much larger map. Not a map with borders or roads, but one where each star is like a point of light scattered across a vast disk. In that map, the sun would sit somewhere about halfway between the centre of the galaxy and its outer edge, not in a particularly special location, just one star among hundreds of billions. And those stars are not packed tightly together. In fact, if you were to move from one star to the next, you would typically travel several light years before encountering another. Most of the galaxy, like most of the solar system, is empty space. But even with that emptiness, the total size of the Milky Way is staggering. From one side to the other, it spans about 100,000 light years. So if light were to begin its journey at one edge and travel straight across to the other, it would take 100,000 years to complete that trip. And that number is worth sitting with for a moment. 100,000 years. That's longer than modern humans have existed in their current form. Longer than written language. Longer than anything we commonly measure in history. If light started crossing the galaxy at a time when early humans were just beginning to explore the world, it would still be travelling today. And yet, even that speed, the fastest possible, is simply what's required to cross the galaxy in the shortest time imaginable. Now let's consider what happens if we slow things down. If instead of travelling at the speed of light, you were moving at the speed of one of our current spacecraft, the journey would take millions of years. Voyager 1, one of the fastest human-made objects, is travelling at about 17 kilometers per second. That sounds fast, and by everyday standards it certainly is. But compared to light, it's incredibly slow. At that speed, crossing the Milky Way would take tens of millions of years, possibly even longer depending on the exact path. That's not just a long trip. That's a journey that would outlast species, continents, climates, entire eras of planetary history. So already, crossing our own galaxy becomes something that stretches far beyond the scale of human experience. But there's another layer to this that makes it even more interesting. The Milky Way is not just a flat disk of stars, it has structure. At its centre lies a dense region known as the galactic core, where stars are packed much more closely together. And at the very centre of that core sits something even more unusual, a supermassive black hole. It's called Sagittarius, a star, and it has a mass millions of times greater than our Sun. It doesn't actively pull in everything around it like some dramatic cosmic vacuum, but its presence shapes the motion of stars near the centre. If you were to travel through the galaxy, your path might take you closer to this central region, where the density of stars increases and gravitational effects become more pronounced. Or you might remain in the quieter outer regions, where stars are more spread out and the environment feels more like what we're used to in our own neighbourhood. Either way, the journey is not uniform. Some regions are denser, more active, filled with star formation, nebulae and energetic events. Others are calmer, more sparse, with long stretches of relatively empty space. So crossing the galaxy isn't just about distance, it's about navigating a varied landscape. one that changes gradually as you move through it. Now, there's another detail worth considering. The Milky Way itself is moving. It rotates slowly but steadily, with stars orbiting the galactic center over incredibly long periods of time. Our Sun, for example, takes about 225 to 250 million years to complete a single orbit around the center of the galaxy. That means that during the time it takes to cross the galaxy at light speed, the entire structure is also shifting. Stars are moving, distances are changing. The galaxy is not a fixed map but a dynamic system, so if you were attempting to cross it, you wouldn't be travelling through something static. You'd be moving through a structure that evolves, slowly but continuously. And yet, despite all of this motion, the overall shape of the galaxy remains recognisable. A spiral with arms that curve outward from the centre, filled with stars, gas and dust. From a distance, it would look almost calm. But from within, it's a vast and complex environment. Now, let's bring this back to the question we've been following. How long would it take to cross the galaxy? At light speed, about 100,000 years. At the speed of our fastest spacecraft, millions of years. At slower speeds, even longer. And this is just one galaxy. Just one among billions. Already the scale has expanded far beyond the solar system, far beyond anything we can easily imagine travelling through. But something else begins to emerge as we consider these numbers. Even though the galaxy is enormous, it is still a single structure. It has boundaries, even if they are somewhat diffuse. It has a centre, a shape, a kind of coherence. And that means that, in principle, it can be crossed. It would take an immense amount of time, but the journey has a beginning and an end. Once you leave one edge, you eventually reach the other. But what happens when we step beyond the galaxy itself? When we move into the space between galaxies, the distances increase again. Not by a small amount, but by another significant leap. Because galaxies are not packed together tightly. They are separated by vast regions of space, where the density of matter drops even further, where the nearest destination might be millions of light years away. So as we continue outward, the question shifts once more. If crossing a single galaxy already takes longer than human history, what does it mean to travel between galaxies? And how long would that take, even for light itself? Once you leave the Milky Way behind, something changes in a way that's difficult to notice at first. There's no clear boundary you pass through, no signpost that says you've officially exited the galaxy. The stars simply begin to thin out. The familiar band of light fades, and eventually, without much ceremony, you find yourself in a region where the night sky would look very different. Not darker exactly, just quieter. Because between galaxies there is very little. This is what we call intergalactic space. And while it might sound like a place filled with dramatic emptiness, it's actually more subtle than that. It's not a complete void. There are still particles drifting through it, mostly hydrogen atoms, a few stray photons, the occasional high-energy particle passing through. But compared to what we experience inside a galaxy, it's incredibly sparse. If you were travelling through this region, you could go vast distances without encountering anything resembling a star system. And that's where the scale shifts again. Inside the Milky Way, stars are separated by a few light years on average. That already felt like a lot. But between galaxies, the distances jump to millions of light years. The nearest large galaxy to us, Andromeda, sits about 2.5 million light years away. That means that if light left the Milky Way and headed straight toward Andromeda, it would take 2.5 million years to arrive. Not because light is slow, but because the distance is immense. And that's just the nearest major galaxy. There are smaller galaxies closer to us, part of what we call the local group, but even those are separated by hundreds of thousands to millions of light years. The local group itself spans several million light years across, containing dozens of galaxies, all loosely bound together by gravity. So even within this relatively small cosmic neighbourhood, distances are already stretching into millions of years of travel time for light. Now imagine leaving the local group entirely. Beyond it, you enter regions of space where galaxies are grouped into larger clusters. One of the nearest is the Virgo cluster, which contains thousands of galaxies and lies about 50 million light-years away. Light travelling from the Virgo cluster takes 50 million years to reach us. That's not just a long journey. That's a journey that began long before humans existed, long before many of the species we know today had even evolved. And yet, even clusters are not packed tightly together. Between them lie even larger regions of space where the density of matter drops further still. These regions are often referred to as cosmic voids. Now, the word void might suggest absolute emptiness, but in reality these areas still contain matter, just far less of it. Galaxies are rare. Stars are almost non-existent. The distances between anything of interest become even greater. If you were travelling through a cosmic void, you might spend tens of millions of years moving without coming close to a single galaxy. It's not just empty, it's quiet in a way that stretches the idea of distance into something almost abstract. And yet, even this emptiness has structure. If you could zoom out far enough, the universe would begin to resemble a kind of web, with galaxies forming along filaments and clusters, and vast voids in between. It's sometimes called the cosmic web, and it gives the universe a kind of large-scale organisation, not organised in a neat geometric way, but in a way that suggests patterns, connections, and immense regions of space where very little happens. So when we talk about travelling between galaxies, we're not just talking about moving from one object to another. We're talking about crossing enormous stretches of mostly empty space, where the journey itself is defined more by distance than by encounters. Now, let's bring this back to the idea of time. If crossing the Milky Way takes 100,000 years at light speed, then crossing the space between galaxies takes much longer. From the Milky Way to Andromeda, 2.5 million years at light speed. From the Milky Way to the Virgo cluster, about 50 million years. And if we extend this to even larger scales, moving between superclusters, the distances can reach hundreds of millions of light years, so even light, moving at the fastest possible speed, spends millions or even hundreds of millions of years travelling through intergalactic space. And that leads to an interesting realisation. Most of the time spent crossing the universe would not be spent inside galaxies. It would be spent between them, in the vast stretches of space where there are no stars nearby, no planets, no familiar reference points, just distance. Now, there's another detail that adds to this picture. The universe is not static. As we've mentioned before, it's expanding, and this expansion becomes more noticeable at larger scales. Galaxies that are very far away are not just distant, they are moving away from us as space itself stretches. The farther away a galaxy is, the faster it appears to be receding. This means that if you were travelling from one galaxy to another, the distance between them might be increasing while you travel. It's not like crossing a fixed gap, it's more like trying to cross a gap that is slowly widening. For nearby galaxies like Andromeda, this effect is small enough that gravity actually pulls the galaxies together, and they are expected to collide in the distant future. But for more distant galaxies, the expansion dominates, and that introduces a kind of limit. There are regions of the universe so far away that, even if you travelled at the speed of light, you could never reach them because the space between you and them is expanding too quickly. We'll explore that idea more carefully later, because it plays a key role in understanding whether crossing the universe is even possible. For now, it's enough to notice that intergalactic space is not just empty. It's dynamic. Distances are not fixed. They change over time. And that means that travel at these scales is not just about how fast you go, but also about how the universe itself evolves while you're on your way. Now, imagine for a moment what it would feel like to travel through this kind of space. There would be long stretches where nothing changes visually, no nearby stars to pass by, no planets to observe, just distant galaxies appearing as faint smudges of light, slowly shifting as you move. Time would pass, not in days or years as we usually think of them, but in spans so long that they lose their usual meaning. Millions of years, tens of millions. And during that time, galaxies themselves would change, stars would form and die, structures would evolve, so the destination you set out toward might not be the same by the time you arrive. This is where the idea of travel begins to feel different, not just longer, but more uncertain. Because when distances are this large, time becomes part of the landscape. The journey is not just through space, it's through the evolution of the universe itself. There comes a point, as we continue stepping outward, where the idea of distance begins to lose its usual meaning. Not because distance stops existing, but because it grows so large that familiar comparisons no longer help. Planets, stars, even galaxies have given us something to anchor to. But beyond a certain scale, there are no more nearby reference points, just everything. And that's where the observable universe comes in. Now, the phrase itself sounds like it should describe the entire universe, but it doesn't quite mean that. It refers only to the part of the universe we can actually see, or more precisely, the part from which light has had enough time to reach us since the beginning. Because the universe has a finite age, about 13.8 billion years, there is a limit to how far light can travel before arriving here. Anything farther away than that distance, its light simply hasn't reached us yet. So when we look out into space, no matter how powerful our telescopes become, there is a boundary beyond which we cannot see. Not because there's nothing there, but because its light hasn't had time to arrive. That boundary is what defines the observable universe. Now, if the universe is 13.8 billion years old, you might expect the observable universe to be about 13.8 billion light years in radius. That would seem like a straightforward conclusion, but here's where things take a slightly unexpected turn. The universe has been expanding during all that time, which means that the objects whose light is reaching us now are much farther away than they were when that light began its journey. So even though the light has been travelling for 13.8 billion years, the galaxies that emitted it are now tens of billions of light years away. When we account for this expansion, the observable universe turns out to be about 93 billion light years across. That's 93 billion light years from one side to the other. And once again, it's worth pausing with that number, not to fully grasp it, because that's nearly impossible, but just to let it settle. Light, moving at the fastest speed allowed by reality, would take 93 billion years to cross that distance, and that's just the part we can see. Now, within this observable universe, there are an estimated 2 trillion galaxies, each one containing billions or even hundreds of billions of stars, each star potentially surrounded by planets, moons, and countless smaller objects. So when we talk about the observable universe, we're not talking about a single structure like a galaxy. We're talking about everything we can observe. All the galaxies, all the clusters, all the voids, all the light that has had enough time to reach us. And yet, even this immense region has a kind of edge. Not a physical boundary you could bump into, not a wall or a surface, but a limit defined by time and light. If you were somehow able to travel toward that edge, you wouldn't encounter a barrier. You wouldn't reach a point where space suddenly stops. Instead, what you would find is that beyond a certain distance there is simply nothing visible. No galaxies, no stars, no structures, just darkness. Not because those things aren't there, but because their light hasn't arrived. So the edge of the observable universe is really an edge of visibility, not an edge of existence. Now, this leads to an interesting question. If you could travel far enough, could you move beyond the observable universe? The answer is complicated. In principle, yes. If you could travel faster than the light that is currently reaching us, you might enter regions that are not yet observable from Earth. But there's a catch. The universe is expanding, and this expansion affects how distances change over time. Some regions of space are receding from us so quickly that their light will never reach us, no matter how long we wait. They are effectively beyond our observable horizon, not just now, but forever. This creates something called a cosmic event horizon, a boundary beyond which events cannot influence us, because the space between us and those events is expanding too quickly. So even if you set out on a journey toward the edge of the observable universe, the destination might not behave the way you expect. As you travel, the observable universe would change. New regions might come into view, while others drift farther away. The edge is not fixed in place. It shifts with time, with motion, with the expansion of space itself. And that makes the idea of crossing the universe a little more subtle, because the universe is not a static map. It's not something you can simply measure once and then travel across. It's evolving. Distances are changing. The very fabric of space is stretching, so the journey you plan at the beginning might not match the reality you encounter along the way. Now, let's return to the question of time. If the observable universe is 93 billion light-years across, then even at the speed of light, the journey from one side to the other would take 93 billion years. That's far longer than the current age of the universe, and that's assuming the universe stops expanding, which it doesn't. In reality, the expansion means that some parts of the universe are moving away from each other faster than light, not because they're travelling through space that quickly, but because space itself is expanding between them. So even light cannot bridge certain distances. This leads to a surprising conclusion. There are parts of the universe that we can see, whose light has already reached us, but which we could never reach, even if we travelled at the speed of light forever. Because by the time we started moving toward them, the expansion of space would carry them away faster than we could approach. So the observable universe is not just large, it's in a sense partially unreachable. Now let's consider what this means for the idea of crossing it. If you imagine starting at one side and travelling to the other, you're imagining a fixed distance, a kind of cosmic road that can be traversed with enough time and speed. But in reality, that road is stretching as you move. Some parts are drifting away faster than you can follow. Others remain within reach, but only for a limited time. So crossing the observable universe is not just a matter of endurance, it's a matter of timing, of understanding how the universe itself changes while you travel. And that adds a layer of complexity to our original question, because now we're not just asking how long it would take to cross a fixed distance, we're asking how long it would take to cross something that is expanding, evolving, and in some cases moving beyond reach. And yet, despite all of this, the observable universe still serves as a useful frame. It gives us a way to talk about the larger scale we can currently measure. It gives us a boundary, even if that boundary is defined by light and time rather than physical edges, and it allows us to begin answering the question in a more concrete way. Because if we know the size of the observable universe, and we know the maximum speed at which anything can travel, we can at least estimate the minimum time required, even if that estimate comes with a few important caveats. Somewhere along the way, the idea of distance quietly shifts from something fixed into something a little more flexible. Up to this point, we've been imagining journeys across space as though the destination is waiting patiently at the other end, like a faraway city you can eventually reach if you just keep going long enough. But the universe has a habit of gently challenging that assumption, because on the largest scales, the universe is not standing still, it's expanding. Now, that word expanding can be a little misleading at first. It doesn't mean that galaxies are flying outward through space like fragments from an explosion. It's not as though there's a central point everything is moving away from. Instead, it's the space between things that is stretching. A helpful way to picture this is to imagine a loaf of bread rising in the oven. As it expands, the raisins embedded within it move farther apart from each other. The raisins themselves aren't growing or travelling through the dough, but the dough between them is expanding, increasing the distance. In this analogy, galaxies are like the raisins and space itself is like the dough. So when we say that the universe is expanding, what we really mean is that the distances between galaxies are increasing over time. And this has a very direct effect on our original question. Because if the universe is expanding, then the distance you're trying to cross isn't constant. It's changing. Now, this expansion was first observed in the early 20th century, when astronomers noticed that distant galaxies appeared to be moving away from us. Not randomly, but in a very specific pattern. The farther away a galaxy is, the faster it appears to recede. This relationship is known as Hubble's law, and it leads to an interesting conclusion. There's no special center to the expansion. From any point in the universe, it would look as though everything else is moving away. Every observer sees the same pattern, with distant galaxies receding faster than nearby ones. So no matter where you are, the universe appears to be expanding around you. Now, at smaller scales, this expansion doesn't dominate. Within galaxies, gravity holds stars together. Within solar systems, gravity keeps planets in orbit. Even within galaxy clusters, gravitational attraction can overcome the expansion of space. That's why the Milky Way isn't stretching apart, and why the planets don't slowly drift away from the Sun. But as we move to larger and larger scales, beyond clusters and into the vast regions between them, the expansion becomes more significant, and eventually it begins to dominate. So if you imagine setting out on a journey across the universe, aiming for some distant galaxy, you're not just travelling through space. You're travelling through space that is stretching while you move. It's a bit like walking across a long, flexible walkway that's slowly extending beneath your feet. You're making progress step by step, but the distance ahead of you is also increasing. Now, if your speed is high enough relative to the rate of expansion, you can still make progress. You can close the gap and eventually reach your destination. But if the expansion is faster than your ability to move through space, then the destination will drift away from you faster than you can approach it. And this is where things become particularly interesting. There are regions of the universe where the expansion is effectively faster than the speed of light. Not because galaxies themselves are moving through space faster than light, but because the space between us and those galaxies is expanding at such a rate that light emitted from them can never reach us. These regions lie beyond what's called the cosmic event horizon, and this horizon marks a kind of limit, not of visibility, but of reachability. Anything beyond this horizon is, in a practical sense, forever out of reach. Even if you could travel at the speed of light indefinitely, you would never catch up. Now, this might sound a bit unsettling at first. The idea that parts of the universe are not just far away, but fundamentally unreachable. But it also helps clarify something important about our original question. When we ask how long it would take to cross the universe, we're assuming that the entire distance is traversable, that given enough time and speed you could start at one point and eventually arrive at another. But because of the expansion of the universe, that assumption doesn't always hold. Some distances grow too quickly, some destinations recede beyond reach, so the finish line is not fixed. It moves, and in some cases it moves away faster than you can follow. Now let's bring this back to a more concrete example. Imagine you're trying to travel to a galaxy that is currently 10 billion light-years away. If the universe were not expanding, and you could travel at the speed of light, it would take 10 billion years to get there. But because the universe is expanding, that galaxy is not staying at a fixed distance. By the time you've travelled for 1 billion years, it might be farther away than when you started. By the time you've travelled for several billion years, it might be so distant that the expansion outpaces your progress. So the total travel time is not just determined by the initial distance, it's affected by how that distance changes over time, and in some cases the journey may never be completed. Now this doesn't mean that all travel is impossible. For nearby galaxies like Andromeda, gravity still dominates over expansion, and the distance between us is actually decreasing. In about 4 to 5 billion years, the Milky Way and Andromeda are expected to merge. So in that case, the finish line is moving closer, not farther away. But as we look farther out, beyond our local group, the expansion becomes more significant, and the balance shifts. Distances increase, travel becomes more difficult, and eventually some regions slip beyond reach entirely. This creates a kind of layered structure to the universe. Nearby regions are accessible, at least in principle. More distant regions are reachable, but require immense amounts of time, and the most distant regions are not reachable at all, no matter how long you travel. So when we think about crossing the universe, we're not dealing with a single, simple journey. We're dealing with a landscape where different parts behave differently. Some areas can be crossed, some can only be approached, and some can never be reached. And all of this is happening while the universe itself continues to evolve. Now, there's one more subtle detail that's worth noticing. The expansion of the universe is not slowing down. In fact, it appears to be accelerating. This acceleration is attributed to something we call dark energy, a form of energy that permeates space and drives the expansion. We don't fully understand what dark energy is, but we can observe its effects. And one of those effects is that distant galaxies are receding faster and faster over time, which means that the cosmic horizon, the boundary of what is reachable, is not just fixed, it's changing. Some galaxies that are currently within reach may eventually drift beyond that horizon as the expansion accelerates. So even the set of destinations that could in principle be reached is not constant. It evolves with time, and that adds another layer to the question. Because crossing the universe is not just about how fast you go, it's about when you go. The earlier you start, the more of the universe remains within reach. The longer you wait, the more of it drifts away. So in a sense, the universe is not just expanding in space, it's expanding in opportunity and in limitation. And that gives our original question a slightly different flavour. It's no longer just a matter of calculating a travel time. It's a matter of understanding a dynamic system, one where distances change, horizons shift, and the very idea of a destination becomes more fluid. So as we continue, it might be helpful to bring things back to something a bit more grounded again. Because while the universe expands and distances stretch in ways that are difficult to imagine, we can still ask a simpler question. If we were to attempt these journeys at speeds we're familiar with, walking, flying, or using our current technology, how quickly would the scale of the universe overwhelm those efforts? And how long would even the smallest steps in this vast journey really take? Consider for a moment something very simple. Not rockets, not spacecraft, not light itself, but just you, moving at a comfortable walking pace. Nothing extraordinary, no advanced technology, just steady steps, one after another, the way humans have travelled for most of history. It sounds almost too simple compared to everything we've been discussing. Galaxies, light years, expanding space. And yet, starting from something so familiar can be surprisingly helpful because it gives us a reference point, a way to anchor all of those enormous distances back to something we actually understand. So let's begin there. A typical walking speed is about 5 kilometers per hour, not rushed, not particularly slow. Just an easy, sustainable pace, the kind you might keep while strolling through a park or heading somewhere without much urgency. If you kept that pace for an entire day without stopping, which already sounds a bit ambitious, you'd cover about 120 kilometers. In a year, assuming you somehow kept going every single day, you'd travel roughly 43,000 kilometers. That's enough to circle the Earth just over once. So already, at a human scale, we can see how distance translates into time. Crossing a planet takes about a year of continuous walking. Manageable in theory, though perhaps a bit tiring in practice. Now let's gently extend that idea outward. The distance from Earth to the Moon is about 384,000 kilometers. At a walking pace, that journey would take nearly 9 years, not accounting for rest, terrain, or the rather obvious lack of a walking path through space. But in terms of raw distance and time, that's the scale. 9 years of walking just to reach the Moon. Now, if we continue onward to the Sun, the numbers change dramatically. The Sun is about 150 million kilometers away. At the same walking pace, that journey would take around 3,500 years, 3.5 millennia. That's longer than most recorded human civilizations. Longer than the time between ancient Egypt and today. and that's still within our own solar system. If we extend the journey out to Neptune, the outermost planet, the distance grows to about 4.5 billion kilometers. Walking that distance would take over 100,000 years. At this point, something begins to shift. The journey is no longer just long. It's no longer something that spans a lifetime or even many lifetimes. It becomes something that stretches across entire eras. Now let's take the next step. Leaving the solar system entirely, we aim for the nearest star, Proxima Centauri, about 4.24 light-years away. A light-year, as we've discussed, is about 9.5 trillion kilometers, so the total distance is roughly 40 trillion kilometers. At a walking pace of 5 kilometers per hour, that journey would take about 900 million years. Nearly 1 billion years. That's longer than complex life has existed on Earth. Longer than the time it took for multicellular organisms to evolve into the diversity we see today. So even reaching the nearest star by walking would take longer than most of Earth's biological history. And yet, this is still just one star. Now imagine continuing. Crossing the Milky Way, which is about 100,000 light-years across, would take on the order of tens of trillions of years at walking speed. Trillions. That's a number so large it begins to lose its meaning in everyday terms. It's far longer than the current age of the universe, which is about 13.8 billion years. So even if you had started walking at the very beginning of the universe, you wouldn't have made it across the galaxy yet. And we're still not at the scale of the observable universe. If we extend this thought experiment to crossing the observable universe, about 93 billion light-years across, the time required becomes almost unimaginable. We're now talking about numbers that exceed the lifetime of stars, the lifespan of galaxies, perhaps even the timescales over which the universe itself changes its structure. At that point, walking ceases to be a meaningful way to think about the journey, not because it's impossible in a strict sense, but because the timescales involved are so vast that the universe itself would evolve many times over before the journey could be completed. Stars would form and die, galaxies would merge, the expansion of the universe would continue, altering distances along the way, so the path you set out on would not remain the same. Now there's something quietly interesting about this. When we think about walking, we think about progress in a very direct way. One step leads to another. Distance decreases steadily. The destination gets closer over time. But at these scales, that intuition begins to break down. Because the universe is not static. As we've discussed, it's expanding. So while you're walking, the distance you're trying to cover is also increasing. And at some point, that expansion would outpace your progress. Which means that no matter how long you walked, some destinations would remain out of reach. Not because you stopped, but because the universe itself changed faster than you could move through it. Now, of course, this is all a thought experiment. Walking through space isn't something we can actually do. There's no ground, no air, no path to follow. But that's not really the point. The point is to take something familiar, something simple, and use it to reveal just how quickly the scale of the universe overwhelms our everyday sense of movement. Because even at a steady, continuous pace, even with no need to rest or stop, the distances involved become too large for human-scale travel to make a meaningful dent. And that tells us something important. The challenge of crossing the universe is not just about distance, it's about scale. The kind of scale that turns years into thousands of years, thousands into millions, and millions into billions. Walking is slow, of course. It's the most basic form of movement. But what if we increase the speed? What if instead of walking, we imagine travelling at the speed of something more familiar in a modern sense? Something like an airplane. How much difference would that make? Would it bring the universe into a more manageable range? Or would the scale still remain far beyond our reach? Instead of steady footsteps, imagine the low hum of engines, the gentle pressure of acceleration, and the sense of covering distance more efficiently. Flying feels fast. It compresses continents into hours and makes the world feel, if not small, then at least manageable. So it's natural to wonder whether that same leap in speed helps when we scale things up. If walking quickly became impractical, perhaps flying brings the universe a little closer to something we can handle. Let's begin with something ordinary. A commercial airplane typically cruises at around 900 kilometers per hour. At that speed, you can cross a continent in several hours, circle the Earth in under 2 days if you don't stop, and reach almost anywhere on the planet within a single day of travel. That's a remarkable improvement over walking. Now let's gently extend that speed outward. The Moon, about 384,000 kilometers away, would take roughly 18 days to reach by airplane. Not quick, but still within a human timescale. You could, in theory, imagine a journey like that, given enough supplies and patience. The Sun, however, sits much farther out. At 150 million kilometers away, flying there at airplane speed would take around 19 years. That's no longer a casual trip. That's a significant portion of a human life, spent continuously in motion just to reach our nearest star. And yet, we're still within the solar system. If we aim for Neptune, about 4.5 billion kilometers away, the journey stretches to over 500 years at airplane speed. 5 centuries. At this point, even flying begins to feel slow, not because the speed itself is unimpressive, but because the distances are growing much faster than our ability to cross them. So let's increase the speed again. Rockets. Modern spacecraft travel much faster than airplanes. The fastest human-made object, the Parker Solar Probe, can reach speeds of around 700,000 kilometers per hour at its peak. That's nearly 200 kilometers per second. Compared to an airplane, that's an enormous jump. Now, we can revisit those same distances. At this speed, the journey to the Moon would take less than an hour. To the Sun, just a few days. To Neptune, a few months. Suddenly the solar system begins to feel more accessible. And this is where things get interesting. Because for the first time, the inner regions of space start to fall within something resembling a manageable time frame. Not easy, not trivial, but within reach of human technology. And yet, even with this dramatic increase in speed, the next step outward quickly reintroduces the scale problem. The nearest star, Proxima Centauri, remains 4.24 light-years away. At the speed of the Parker Solar Probe, it would take over 6,000 years to get there. 6,000 years. That's longer than recorded human history. Longer than the time since the earliest civilizations began to form. So even with our fastest current technology, reaching the nearest star is not a short journey. And crossing the Milky Way, at these speeds, it would take on the order of hundreds of millions of years. Not thousands, not millions, hundreds of millions. A timescale comparable to the age of complex life on Earth. And if we extend that to crossing the observable universe, the numbers grow so large that they stop being useful in a practical sense. We're now dealing with durations that far exceed the age of the universe itself. So what does this tell us? It tells us that while increasing speed helps, it doesn't solve the problem. Each step up in speed makes a noticeable difference at smaller scales. Walking to flying, flying to rockets. The improvements are real, and they matter within the solar system. But once we step beyond that, into interstellar and intergalactic distances, even our fastest machines begin to look slow. Now, there's another detail worth considering. Real technology isn't just about speed, it's about sustainability. Airplanes need fuel, rockets need energy, spacecraft require careful planning, navigation, and resources to operate over long periods of time. So even if we could build a spacecraft capable of travelling at extreme speeds, maintaining that journey over thousands or millions of years introduces challenges that go far beyond propulsion. Life support, materials, navigation, communication, all of these become limiting factors. And that's before we even consider the environment. Space is not entirely empty. There are particles, dust, and radiation. At very high speeds, even tiny particles can pose significant risks because the energy of an impact increases dramatically with speed. So travelling faster is not just about going quicker, It's about managing the consequences of that speed. Now, there are concepts that push beyond our current technology, ideas like nuclear propulsion, ion drives, or even more speculative systems that could reach a fraction of the speed of light. Some proposed designs suggest spacecraft travelling at 10% or even 20% of light speed. At those speeds, the journey to Proxima Centauri could take a few decades instead of thousands of years. That begins to feel more manageable, but even then, crossing the galaxy would still take hundreds of thousands of years, and crossing the observable universe would still require billions of years. So even when we stretch our imagination to include technologies far beyond what we currently have, the scale of the universe remains dominant. Speed helps, but distance still wins. Now, there's something quietly revealing about this. Each time we increase speed, we expect the problem to shrink, and it does, but only up to a point. Beyond that, the distances grow faster than our improvements. If walking is too slow and flying is still too slow, and even our fastest spacecraft are not nearly fast enough, then perhaps the real key lies elsewhere. Not just in how fast we go, but in what happens as we approach the ultimate speed limit. The speed of light. Because as we get closer to that speed, something unusual begins to happen. Not just to distance, but to time itself. And that changes the nature of the journey in a way that isn't immediately obvious. So instead of asking how long the journey takes from the outside, we might begin to ask a different question. How long would the journey feel from the inside? Imagine for a moment that all the limitations we've been working around quietly fall away. Not in a dramatic, unrealistic sense, but just enough to allow one simple change. Instead of walking, flying, or riding aboard even the fastest spacecraft, you are now moving at the speed of light, not approaching it, not nearly reaching it, exactly at that speed. It's a strange idea, because as we mentioned earlier, anything with mass cannot actually do this. So rather than thinking of yourself as a physical traveller in the usual sense, it helps to imagine that you are simply carried along at that speed, following the same path that light would take. And this is where something very interesting begins to happen. Because from our usual perspective, the speed of light gives us a clear way to measure distance. A light year is how far light travels in a year. So if something is 10 light years away, it takes light 10 years to get there. That feels straightforward. But from the perspective of something moving at the speed of light, the experience is completely different. In fact, from that perspective, time does not pass at all. Now, that might sound like a contradiction at first. How can a journey take years, thousands of years, or billions of years, and yet also take no time at all? The answer lies in how time and motion are connected. As something moves faster and faster, approaching the speed of light, time for that object slows down relative to an outside observer. This is time dilation, something we touched on earlier. At everyday speeds, the effect is so small that we don't notice it. But as you get closer to the speed of light, the effect becomes more pronounced. And at the speed of light itself, time effectively stops. Which means that from the point of view of light, the moment it begins its journey and the moment it ends are the same moment. No waiting, no duration, no passage of time. So if you were somehow able to ride light, to move at that exact speed, the entire journey across any distance would feel instantaneous. Now, let's carefully connect that idea back to the universe. From our perspective, crossing the solar system at the speed of light takes hours to a year, depending on how far you go. Crossing the Milky Way takes 100,000 years. Travelling between galaxies takes millions of years. Crossing the observable universe takes tens of billions of years. Those numbers are all measured from the outside, from the perspective of an observer who's not moving at light speed. But from the perspective of light itself, none of those durations exist. The entire journey, no matter how large the distance, happens in a single, indivisible moment. And that leads to a very unusual way of thinking about travel. Because normally, when we imagine a journey, we think about time passing. We think about the experience of moving, the progression from one place to another, the sense of distance being gradually reduced, but at light speed that sense of progression disappears. There is no gradual movement, no ticking clock, no sense of getting closer. Only the starting point and the ending point effectively collapsed into one. Now, this doesn't mean that distance itself disappears. From our perspective, the distance is still there. It still takes light billions of years to cross the universe. But for the traveller moving at that speed, distance and time become intertwined in a way that removes the usual experience of travel. And this brings us to an important distinction. There are two ways to measure a journey. One is from the outside, asking how long it takes in the universe's frame of reference. The other is from the inside, asking how long it feels for the traveller. At light speed, those two answers become completely different. From the outside, the journey across the observable universe takes tens of billions of years. From the inside, it takes no time at all. Now, of course, this raises an interesting question. If the journey feels instantaneous, does that mean you could effectively cross the universe instantly? In one sense, yes, but in another sense, not quite. Because from the perspective of everyone else, from the rest of the universe, the journey still takes time. Billions of years pass while that light travels. So while the traveller experiences no time, the universe itself continues to evolve. Stars form and die, galaxies merge, distances expand. So if you were to arrive at the other side of the universe, you wouldn't be arriving in the same universe you left. You would be arriving in a future version of it, one that has changed over immense spans of time. And this is where the idea of crossing the universe becomes a little more nuanced. Because the journey is not just about distance, it's about time as well. Now let's take a slightly different angle on this. Instead of imagining yourself moving exactly at the speed of light, imagine travelling very close to it. Not quite reaching it, but getting extremely close. At these speeds, time dilation becomes very significant. From the perspective of someone on Earth, your journey might take thousands or millions of years, but from your own perspective, the time experienced during the journey could be much shorter. Years instead of millennia. Days instead of years, if you get close enough. So even though you're not at light speed, you're still benefiting from the same effect. Time stretches differently for you. And this opens up an interesting possibility. While we cannot reach the speed of light, and therefore cannot eliminate travel time entirely, we can, in principle, reduce the experienced duration of a journey by travelling at very high speeds. So from the traveller's point of view, the universe could feel much smaller than it appears from the outside. A journey across the galaxy might feel like a lifetime, rather than 100,000 years. A journey across larger distances might still be long, but not as impossibly long as the outside perspective suggests. We'll explore that idea more carefully in the next part, because it leads to some very interesting consequences. For now, it's enough to notice something simple. Light gives us a kind of ultimate reference point. It shows us the fastest possible way to move through space. It defines the minimum time required for any journey, from the outside perspective, and at the same time it reveals something deeper about the relationship between space and time, that they are not separate, that they can stretch, compress, and behave differently depending on how you move. So when we ask how long it would take to cross the universe, light gives us two answers. From the outside, billions of years. From the inside, no time at all. And somewhere between those two perspectives lies the experience of any traveller moving at speeds we can actually approach. Not instantaneous, but not fixed in the way we might expect either. If travelling close to the speed of a light changes how time is experienced, what does that mean for someone actually making that journey? How would time pass for them compared to the rest of the universe? Something subtle begins to change the moment we stop thinking about time as something universal and start treating it as something that can differ depending on how you move. Up to now, it's been convenient to imagine that a second is always a second, that time flows at the same steady pace for everyone, everywhere. That assumption works perfectly well for everyday life. It keeps clocks synchronized, schedules predictable, and conversations coherent. But once motion reaches extreme speeds, especially speeds approaching that of light, time quietly loosens its grip on that idea. It begins to behave differently, and this is where relativity becomes less of an abstract concept and more of a very practical part of the journey. Let's ease into this gently. Imagine two identical clocks. One remains on Earth, sitting still, ticking away at a steady pace. The other is placed on a spacecraft that accelerates to an extremely high speed, something close to the speed of light. Both clocks start at the same moment, perfectly synchronized. From the perspective of someone watching from Earth, the moving clock begins to tick more slowly. Not because it's malfunctioning, not because something has gone wrong with the mechanism, but because time itself is passing differently for the moving system. This effect, time dilation, is one of the central results of Einstein's theory of special relativity, and while it might sound unusual, it has been tested and confirmed in many experiments. Highly precise atomic clocks placed on fast-moving aircraft tick slightly slower than identical clocks left on the ground. Particles travelling at high speeds in accelerators live longer than they would at rest, because their internal clocks are running more slowly relative to us. So this is not just a theoretical idea, it's something that actually happens. Now, at everyday speeds, the effect is extremely small. You wouldn't notice it in a car, or even in a commercial airplane. But as speed increases, the effect becomes more pronounced, and as you approach the speed of light, it becomes dramatic. So let's connect this to our journey. If you were travelling across space at a very high speed, something close to the speed of light, time for you would pass more slowly compared to time for someone who remained stationary. From your perspective, your clock would feel perfectly normal. Seconds would tick by as they always do. Your heartbeat, your thoughts, everything would feel unchanged. But from the perspective of someone watching from Earth, your clock would appear to slow down. And the faster you move, the greater the difference. Now, here's where it becomes particularly interesting. Imagine you set out on a journey to cross the Milky Way. From the outside perspective, at the speed of light, that journey takes about 100,000 years. But if you travel at a speed very close to light speed, time dilation means that from your perspective, the journey could take much less time. Years, perhaps decades, depending on how close you get to that ultimate speed. So while the universe outside your spacecraft experiences 100,000 years passing, you might experience only a small fraction of that. And that changes the nature of the journey completely. Because now the question, how long does it take, has two answers, one for the observer, one for the traveller. Now, let's take this idea a step further with a classic thought experiment. Two identical twins. One stays on Earth, the other boards a spacecraft and travels at a very high speed, eventually returning home. From the perspective of the twin on Earth, many years have passed, but for the travelling twin, fewer years have passed. When they reunite, the travelling twin is younger than the one who stayed behind. This is often called the twin paradox, though it's not really a paradox once you understand the details. It's a natural consequence of how time behaves at high speeds, and it illustrates something important. Time is not absolute, it depends on motion. Now, let's bring this back to the idea of crossing the universe. If you are able to travel at speeds close to the speed of light, then from your perspective, even very large distances could be crossed in relatively short amounts of time. A journey to a distant star might feel like a few years. A journey across the galaxy might feel like a lifetime. Even larger journeys might still be long, but not impossibly so from your own point of view. But there's a trade-off. While you experience a shorter duration, the universe outside your journey continues to evolve. By the time you arrive, much more time has passed for everyone else. So if you set out on a journey that takes, from your perspective, 10 years, it might correspond to thousands or even millions of years in the rest of the universe. And that leads to an interesting consequence. You could, in a sense, travel into the future. Not by jumping directly to a different time, but by moving in such a way that time passes more slowly for you than for others. When you arrive, you would find yourself in a future that you did not fully experience along the way. Now, there's another aspect of relativity that becomes relevant here: length contraction. As an object moves at very high speeds, distances in the direction of motion appear to shrink from the perspective of the traveller. So not only does time pass differently, but space itself is measured differently. From your point of view, the distance you need to travel becomes shorter. This works together with time dilation. The faster you go, the more time slows down for you, and the more distances contract along your direction of travel. So the universe, from your perspective, becomes compressed. Not physically in the sense that everything shrinks in an absolute way, but in the way it is measured within your frame of reference. And this is how it becomes possible, at least in principle, for a traveller moving near the speed of light to cross vast distances in what feels like a relatively short time. But again, this is all relative. From the outside, the journey still takes the full duration. From the inside, it feels much shorter. Now there's an important detail to keep in mind. Reaching speeds close to the speed of light requires enormous amounts of energy. The closer you get to that speed, the more energy is needed to accelerate further. So while these effects are real, achieving the conditions where they become significant is extremely challenging. But as a thought experiment, they reveal something fundamental. Time and space are not fixed. They are part of a connected system, and motion through that system changes how they are experienced. So when we ask how long it would take to cross the universe, relativity tells us that the answer depends on how you travel. At everyday speeds, the journey is unimaginably long. At speeds close to light, the journey could feel much shorter for the traveller. But in all cases, the universe itself continues to evolve over its own timescale. So the destination you reach is not the same as the one you left behind. And that adds another layer to the idea of crossing the universe. Because it's not just about distance and time, it's about how those two are connected, and how they change depending on your motion. It might be worth asking a slightly more personal version of the question. If two travellers take different paths through space and time, how do their experiences compare, and what happens when they meet again? Picture two people who begin in exactly the same place, at exactly the same moment, with identical clocks, identical ages, and identical expectations about how time should pass. There's nothing unusual about them at the start. If you place them side by side, you wouldn't be able to tell them apart. Now imagine that one of them stays where they are, somewhere calm and familiar, perhaps on Earth or in a quiet orbit nearby. The other, however, decides to leave, not in a hurry, not recklessly, but with a clear intention to travel very, very fast. Fast enough that the effects we've been describing, time dilation, and the shifting relationship between space and time, begin to play a noticeable role. So the traveller boards a spacecraft, accelerates gradually, and eventually reaches a speed that is extremely close to the speed of light, and then they go. At first, nothing feels particularly different from their own perspective. The clock inside the spacecraft ticks normally. Their heartbeat, their thoughts, their sense of time all feel unchanged. If they look around, everything behaves exactly as expected. There's no sensation of time slowing down, no obvious distortion in the moment-to-moment experience. From the inside, time always feels normal. But from the outside, from the perspective of the person who stayed behind, something very different is happening. The traveller's clock appears to tick more slowly, not by a large amount at first, but as the speed increases, the difference becomes more noticeable, and at speeds very close to light, it becomes dramatic. Years for the traveller might correspond to decades, centuries, or even longer for the observer who remains at rest. So as the journey continues, the two timelines begin to drift apart. Now, let's imagine that the traveller doesn't just go for a short trip, but continues outward for a long time, perhaps crossing large portions of the galaxy, or even venturing into intergalactic space. From their own perspective, the journey might take a manageable amount of time, years, perhaps decades. Long, certainly, but still within a single lifetime. They would experience the trip as a continuous sequence of moments, just like any other journey. They would see distant stars approach, pass by, and recede behind them. They might observe galaxies shifting slowly as they move. Everything would feel consistent. But for the person who stayed behind, time would be passing much more quickly. While the traveller experiences, say, 20 years, the observer might experience thousands, millions, or even more, depending on the speed and duration of the journey. And this leads us to the moment when the traveller returns, because eventually, in this thought experiment, the traveller turns around and comes back. Not instantly, of course. The return journey also takes time, and the same effects apply. Time continues to pass more slowly for the traveller compared to the observer, so by the time they arrive back at their starting point, something remarkable has happened. The traveller has aged only a small amount, but the world they return to has aged much more. If the observer was their twin, identical at the start, the difference would now be clear. One is significantly older than the other, and not because of any biological difference, not because one lived more carefully or more slowly, but because they moved through space at different speeds. This is what we mean when we say that time is relative. It's not just a philosophical idea. It has real, measurable consequences. Now, there's an important detail here that's worth clarifying, because it often causes confusion. From the traveller's perspective, it might seem like the observer is the one moving away, and therefore their clock should be the one that slows down. So why does the traveller end up younger? The answer lies in the fact that the traveller changes frames of reference during the journey. They accelerate when they leave, decelerate, turn around, and accelerate again to return. These changes break the symmetry between the two situations. The observer who stays behind remains in a relatively consistent frame of reference, while the traveller does not. And that difference is what leads to the aging discrepancy. So the result is not a contradiction, it's a natural outcome of how motion and time are connected. Now, let's bring this back to the idea of crossing the universe. If you were to travel across vast distances at speeds close to the speed of light, the same effect would apply. From your perspective, the journey might feel manageable. You could, in principle, cross the galaxy within a lifetime, if you moved fast enough. But when you arrived, the universe would not be the same as when you left. Not because you travelled to a different place, but because you also travelled into the future. Time passed differently for you. So crossing the universe is not just a journey through space, it's a journey through time. And the faster you go, the more pronounced that effect becomes. Now imagine extending this idea even further. Suppose you set out on a journey that, from the outside perspective, takes millions or billions of years. But because you are travelling at a speed very close to light, you experience only a fraction of that time. When you arrive, you would find yourself in a universe that has aged enormously. Stars that once existed might be gone. Galaxies might have merged or shifted. The large-scale structure of the universe might be different. So even though you travelled a specific distance, the context of that distance has changed. The destination is not just far away, it's also far in the future, and this changes the meaning of arrival, because you're not arriving at the same moment in the universe that you left. You're arriving at a later stage of its evolution. Now there's something quietly profound about this. It means that high-speed travel is not just a way of moving through space more efficiently. It's also a way of moving through time, not in the sense of going backward or revisiting the past, but in the sense of skipping forward relative to others, experiencing less time while the universe experiences more. And that creates a kind of separation between the traveller and the rest of the universe, not a physical separation, but a temporal one. Now let's return to the twins. At the end of the journey, when they stand side by side again, they share the same space, but not the same history. One has lived through a long stretch of the universe's timeline, the other has experienced only a small portion of it, and yet both experiences are valid. Both are real. Because time is not something that happens the same way for everyone. It depends on how you move. So when we ask how long it would take to cross the universe, we have to be careful about what we mean. From one perspective, the journey might take billions of years. From another, it might feel much shorter. But in all cases, the universe itself continues to evolve, and that means that crossing the universe is never just about distance. It's about how that distance is experienced, and how time unfolds along the way. Now, there's another aspect of the journey we haven't explored yet, because moving at such high speeds, across such vast distances, is not just a question of time and motion. It also raises practical challenges. What happens when you encounter matter along the way? What risks are involved in travelling through space at these speeds, and what might actually stand in your path as you attempt such a journey? Drifting outward through space might sound like the simplest kind of journey imaginable. No traffic, no terrain, no weather to worry about. Just a straight path through emptiness, uninterrupted and quiet. Compared to crossing oceans or navigating mountains, it almost feels like space should be the easiest place to travel. But that calm appearance is a little misleading, because even though space is incredibly empty, the few things that are out there begin to matter a great deal once you start moving very fast, and the faster you go, the more those small things become not exactly obstacles in the traditional sense, but something you can't ignore. Let's begin with something that seems almost insignificant: dust. Not the kind you might find on a shelf or floating in sunlight, but tiny particles scattered throughout space. These grains are often smaller than a grain of sand, sometimes closer to the size of smoke particles. They drift between stars left behind by dying stars' collisions and the slow processes that shape galaxies over time. On their own, these particles don't do much. If you were floating gently through space at a slow speed, they would barely register. You might pass through them without noticing at all, but as your speed increases, something changes. The energy of a collision depends not just on the size of an object, but on how fast you're moving when you hit it. At very high speeds, even a tiny particle can carry a surprising amount of energy. If you are travelling at a significant fraction of the speed of light, even something as small as a grain of dust could strike with the energy of a small explosion. Not because the particle itself is large, but because of the speed involved. So while space is mostly empty, the few particles that are present become increasingly important as your speed increases. And that means that travelling across the universe is not just about moving fast, it's also about protecting yourself from what you might encounter along the way. Now, dust is only one part of the picture. There's also radiation. Space is filled with high-energy particles, often referred to as cosmic rays. These particles originate from various sources, including supernova explosions, active galaxies, and other energetic events. They travel at very high speeds, sometimes close to the speed of light themselves. At low levels, radiation is something we can manage. Spacecraft are designed with shielding to protect both equipment and, in some cases, people from exposure. But over long periods of time, and especially at high speeds, the exposure becomes more significant. Because as you move faster, the rate at which you encounter these particles increases. From your perspective, more and more radiation is coming toward you, simply because you're moving through space more quickly. And that adds to the challenge. Not just reaching your destination, but maintaining the conditions necessary to survive the journey. Now let's consider something a bit larger. Not dust, not individual particles, but entire regions of space where matter is more concentrated. Nebulae, for example. These are vast clouds of gas and dust, often spanning dozens or even hundreds of light years. Some are the birthplaces of new stars, regions where matter gathers and begins to collapse under gravity. If you were travelling through the galaxy, you might pass through such a region, and while the density of a nebula is still very low compared to anything we experience on Earth, it's higher than the surrounding space. So at high speeds, moving through a nebula would mean encountering more particles, more interactions, more potential impacts. Again, not an obstacle in the sense of a wall or barrier, but something that affects the journey. Now let's turn to gravity. Gravity is everywhere in the universe. Every object with mass exerts a gravitational pull, from tiny particles to massive galaxies. At small scales, gravity might not seem like much of a concern. But as you move through space, especially near large objects, it becomes more significant. If your path takes you near a star, a planet, or a black hole, the gravitational field can alter your trajectory. It can pull you off course, accelerate you, or in some cases trap you entirely. This is something spacecraft already use to their advantage. Gravity assists, for example, allow spacecraft to gain speed by passing near planets, using their gravitational pull to change direction and increase velocity. But on a larger journey, especially one that spans the galaxy or beyond, gravity becomes something you need to navigate carefully. Because not all gravitational encounters are helpful. Some can be dangerous. Black holes, for instance, represent extreme gravitational environments. If you were to pass too close to one, the tidal forces, the difference in gravitational pull across your body, could become very strong enough to stretch and distort objects in ways that are difficult to imagine. Even at safer distances, the presence of a black hole can influence the motion of nearby matter, creating complex and dynamic regions of space. So as you travel, you would need to account for these gravitational influences, adjusting your path to avoid unwanted encounters. Now, there's another subtle effect worth mentioning. At very high speeds, your interaction with space itself changes. From your perspective, particles and radiation ahead of you become more concentrated and more energetic. This is due to relativistic effects, where motion at high speed alters how you perceive incoming matter and energy. So not only are you moving through space, but space is, in a sense, coming toward you more intensely, which means that shielding, navigation, and awareness of your environment become increasingly important. Now let's step back for a moment and consider what all of this means. Space is mostly empty. That part is true, but it's not completely empty. And when you're moving at high speeds, even small amounts of matter and energy become significant. So the journey across the universe is not just about covering distance, it's about managing interactions with dust, with radiation, with gravitational fields, and all of these factors add layers of complexity to the idea of travel. Because it's not enough to simply go fast, you need to go safely, you need to maintain your path, you need to account for the environment you're moving through. And that environment, while sparse, is not entirely passive. Now there's one more aspect to consider: time. As we've discussed, at very high speeds, time behaves differently. But these environmental factors, dust, radiation, gravity, still operate within the broader framework of the universe. So even if your journey feels short from your perspective, you're still interacting with a universe that evolves over much longer timescales, which means that the conditions you encounter might change as you travel. Regions of space that are quiet at one moment might become more active later. Stars might explode, galaxies might merge. So the journey is not just through space, but through a dynamic, changing environment. Now all of this might make the idea of crossing the universe feel more complicated, and in many ways it is, but it also highlights something important. The challenge is not just distance, it's everything that comes with that distance. The interactions, the environment, the physics that governs how you move and what you encounter. Moving at high speeds, protecting against dust and radiation, and navigating gravity all require energy. A lot of it. And that raises another question. How much energy would it actually take to make such a journey? And is that energy something we could realistically obtain? Even before you begin to move, before the first moment of acceleration, before any dust or radiation or distant gravity comes into play, there is a quieter question waiting at the very start of the journey. How do you get up to speed? It sounds simple when phrased like that. We're used to accelerating things all the time. Cars speed up, planes take off, rockets launch. The idea of going faster is something we understand quite well, but as we gently push that idea toward the speeds we've been discussing, something changes in a way that isn't immediately obvious. Because speed, especially very high speed, is not just about motion. It's about energy. And not just a little more energy, a lot more. Let's begin with something familiar again, just to keep the footing steady. If you push a bicycle, it starts moving. Push harder, and it goes faster. If you keep applying force, you can increase its speed gradually. The relationship feels straightforward. More effort, more speed. Now imagine doing the same with a car. It takes more energy to accelerate than a bicycle, because it has more mass. But the idea still holds. With enough fuel, enough force, you can keep increasing the speed. Rockets follow the same basic principle. They burn fuel, expel it in one direction, and accelerate in the opposite direction. The more fuel they carry, the longer they can accelerate, and the faster they can go. So far, everything behaves in a way that feels intuitive. But as you start approaching the speed of light, this intuition begins to break down. Not suddenly, but gradually. At first, the increase in energy required to go faster feels manageable. Doubling your speed requires more energy, but it's still within the realm of possibility. But as you continue to increase speed, the amount of energy required grows faster than you might expect, and eventually it begins to grow dramatically. This is because of the way motion works at very high speeds. As an object moves faster, its resistance to further acceleration increases, not because its mass is physically increasing in the everyday sense, but because of how energy and momentum behave under the rules of relativity. So each additional increase in speed requires more energy than the last, and the closer you get to the speed of light, the more extreme this effect becomes, until you reach a point where the energy required to increase your speed further becomes enormous. And then, as you approach the speed of light itself, the required energy approaches infinity, which means that reaching the speed of light is not just difficult, it's impossible. Not because we lack the right technology, but because the amount of energy required would be infinite. And that's not something you can gather, store, or generate. Now, let's put some numbers to this idea, not to overwhelm, but to give a sense of scale. The energy required to accelerate an object increases roughly with the square of its speed at lower velocities. But as you approach light speed, the relationship becomes much steeper. Even getting to a fraction of the speed of light requires an enormous amount of energy. For example, accelerating a spacecraft to 10% of the speed of light would require energy comparable to the total energy consumption of entire nations over long periods of time. At 50% of the speed of light, the energy required becomes vastly larger, and at 90% or 99% of the speed of light, the energy requirements grow to levels that are difficult to meaningfully compare to anything we currently produce. Now this is just for acceleration. We haven't even considered the energy needed to slow down at the destination, because if you accelerate to a very high speed, you also need to decelerate if you want to arrive rather than simply pass by. So in many cases, the total energy requirement is effectively doubled. Now, there's another factor that makes this even more challenging: fuel. Rockets carry their own fuel, and that fuel has mass. So if you want to accelerate to high speeds, you need to carry a large amount of fuel. But that fuel itself adds to the mass of the spacecraft, which means you need even more energy to accelerate it, which requires more fuel, which adds more mass, and so on. This creates a kind of feedback loop. More speed requires more energy requires more fuel increases mass, more mass requires even more energy, and this quickly becomes impractical. There's a well-known equation in rocketry that describes this relationship, and it shows that the amount of fuel required increases exponentially with the desired speed. So to reach even a modest fraction of the speed of light, the amount of fuel needed becomes enormous, far beyond what we can currently manage. Now there are ideas that try to get around this problem. Some concepts involve using external energy sources such as lasers or particle beams to push a spacecraft without requiring it to carry all its own fuel. Others explore more efficient propulsion methods like nuclear fusion or antimatter reactions, which could provide much more energy per unit of mass than chemical fuels. These ideas are interesting, and some are being actively studied. But even with these advanced concepts, the energy requirements remain extremely high. And that brings us back to the central point. the challenge of crossing the universe is not just about distance, it's about the energy required to move across that distance at meaningful speeds. Even if we could build a spacecraft capable of withstanding the journey, even if we could navigate the obstacles along the way, we would still need a way to supply and manage the energy required for acceleration. And that energy, especially at speeds approaching light, is immense. Now there's another subtle aspect to consider. Energy is not just a practical limitation, it's also tied to the structure of the universe itself. The speed of light is not just a speed limit for motion, it's also a reflection of how energy, mass, and space-time are connected. So when we talk about the difficulty of reaching that speed, we're really talking about the fundamental nature of reality. It's not just that we don't have enough fuel, it's that the rules of the universe make it increasingly difficult to push beyond certain limits. Now this doesn't mean that all hope is lost. It simply means that if we want to think about crossing the universe, we may need to consider different approaches, not just going faster in the traditional sense, but perhaps changing how we think about distance itself. And that's where some of the more speculative ideas come into play. Concepts like wormholes, warp drives, and other ways of altering the geometry of space rather than moving through it in the usual way. These ideas are still theoretical, and they come with their own challenges, but they offer a different perspective. Instead of asking how much energy is needed to go faster, they ask whether it's possible to shorten the path, to bring distant points closer together rather than trying to cross the entire distance. Now, whether those ideas are physically possible is still an open question, but they highlight something important. The problem of energy is not just about building bigger engines, it's about understanding the limits imposed by the universe and finding ways, if possible, to work within those limits. So as we continue, it might be worth exploring those alternative ideas. If going faster becomes impractical due to energy constraints, could there be a way to travel differently? Not by increasing speed, but by changing the path itself? And what would that mean for our original question? How long would it take to cross the universe if the distance itself could be adjusted? Every now and then, when distance starts to feel overwhelming, there's a natural instinct to look for a shortcut. Not by going faster, not by pushing harder, but by asking a slightly different question. What if you didn't have to cross the entire distance at all? It's the same kind of thought that comes up in everyday life. If two cities are far apart, you don't always travel in a straight line. You look for bridges, tunnels, routes that reduce the effort. You change the path instead of increasing the speed. And when we bring that idea into the scale of the universe, it leads to something that feels almost like science fiction, but actually comes from the same physics we've been discussing: wormholes. Now the name itself sounds a little unusual, but the idea behind it is quite simple once you step into it slowly. Imagine space not as an empty void, but as something that has structure. Not solid, not something you can touch in the usual sense, but something that can be shaped, stretched, and curved. This is already part of how we understand gravity. Mass bends space. That's why planets orbit stars, why stars orbit galaxies, why everything follows curved paths rather than straight lines when gravity is involved. So if space can be curved, then in principle it can also be curved in more complex ways, and this is where the idea of a wormhole comes in. Instead of travelling from one point to another across a long, stretched-out path, a wormhole would connect two distant points directly, like a tunnel, a shortcut. If you imagine a sheet of paper with two dots drawn far apart, the usual way to travel between them is to move along the surface of the paper, but if you fold the paper so that the two dots touch, the distance between them becomes effectively zero. A wormhole is something like that. Not folding paper, of course, but bending space in such a way that two distant regions become directly connected. So instead of travelling across billions of light years, you could, in principle, step through a wormhole and emerge on the other side almost instantly. Now that sounds like it solves everything. Distance becomes irrelevant. Travel time drops dramatically. The universe becomes, in a sense, much smaller. But as with many things, the details matter. Because while wormholes are allowed as solutions in the equations of general relativity, that doesn't mean they're easy to create, or even that they naturally exist in a usable form. One of the main challenges is stability. A simple wormhole, if it were to form, would likely collapse almost instantly. The structure would pinch off before anything could pass through. To keep a wormhole open, you would need something called exotic matter. This is not just ordinary matter. It would need to have unusual properties such as negative energy density, something that behaves very differently from anything we commonly encounter. And while certain quantum effects hint that such conditions might be possible in very small controlled situations, we don't currently have any way to produce or manage exotic matter on the scale needed to stabilize a wormhole. So even though the idea is mathematically consistent, the practical challenges are enormous. Now, let's imagine, just for the sake of understanding, that a stable wormhole could exist. What would travel through it feel like? From your perspective, the journey could be extremely short. You might enter one side and exit the other almost immediately, with no sense of crossing the vast distance in between. From the outside, however, the two ends of the wormhole could be separated by billions of light years, so the shortcut doesn't eliminate the distance, it bypasses it, and that's an important distinction. Because it means that the universe itself hasn't changed, the distance is still there, but your path through it is different. Now there's another interesting consequence of this idea. If wormholes connect distant points in space, they could also, under certain conditions, connect different points in time. This is where things become even more complex. Because if the two ends of a wormhole experience time differently, due to motion or gravitational effects, then travelling through the wormhole could, in principle, allow you to arrive at a time different from when you left. This leads to the possibility of time travel, at least in theory. But it also introduces a number of paradoxes and complications that make the situation much less straightforward. So while wormholes offer a way to cheat distance, they don't necessarily simplify everything. They shift the problem into a different domain. Now there are other ideas that explore similar concepts, warp drives for example. Instead of creating a tunnel through space, a warp drive would involve compressing space in front of a spacecraft and expanding it behind. So the spacecraft itself wouldn't be moving through space faster than light. Instead, the space around it would be moving, carrying the spacecraft along. This is another way of getting around the speed limit, not by breaking it, but by redefining what it means to move. And like wormholes, warp drives are based on real solutions to the equations of general relativity. But they also come with significant challenges. They require enormous amounts of energy, possibly even more than what we discussed earlier. And they may also require exotic forms of matter or energy that we don't yet know how to produce. So once again, we find ourselves in a situation where the idea is theoretically possible but practically uncertain. Now stepping back from the technical details, there's something interesting about all of this. When we ask how long it would take to cross the universe, we naturally assume that the distance must be travelled in the usual way, step by step, or metre by metre, or light year by light year. But these ideas suggest that the question itself might be flexible. Maybe the challenge is not just about speed, maybe it's about the path. If you can change the path, if you can connect distant points directly, then the meaning of distance changes, and with it, the meaning of travel time. Now whether these ideas can ever be realised is still an open question. They may remain theoretical, or they may one day become part of our technological capabilities. But even as thought experiments, they help us see the problem from a different angle, because they remind us that the universe is not just a collection of distances, it's a structure governed by rules. And sometimes, understanding those rules opens up possibilities that are not immediately obvious. So instead of asking only how fast we can go, we begin to ask how space itself might be shaped, and whether there are ways to move through it that are fundamentally different from what we're used to. So even if you could reduce the distance, even if you could find a shortcut, would there ever be a point where you could truly say you've crossed the universe? Or does the universe itself continue to grow beyond any journey you might attempt? Try to picture setting out toward a destination that refuses to stay still. Not in a dramatic way, not darting off unpredictably, but drifting, steadily, quietly, always just a little farther than it was a moment ago. You keep moving, making progress, watching the distance ahead change, and yet something about the situation feels different from any journey we're used to. Because here, the destination is not waiting, it's receding. Up to this point, we've been able to imagine journeys with a kind of structure. There's a starting point, a path, and an end point. Even when the distances were enormous, there was still the sense that, given enough time and the right conditions, you could eventually arrive. But when we take the expansion of the universe seriously, especially at the larger scales, that assumption begins to soften. Because the universe is not just expanding, it's continuing to expand while you travel. And that means the idea of arrival becomes a little less straightforward. Let's ease into this step by step. When we say the universe is expanding, we mean that the distances between distant galaxies are increasing over time. The farther away something is, the faster it appears to move away from us, not because it's flying through space, but because space itself is stretching. Now, at smaller scales, this effect is almost invisible. Within our galaxy, gravity keeps stars bound together. Within galaxy clusters, gravity still has a strong influence. Even between nearby galaxies, like the Milky Way and Andromeda, gravity can overcome the expansion and bring them closer together. So in those cases, travel still behaves in a familiar way. The destination might be far, but it's not running away faster than you can approach it. But as we look farther out, something changes. Beyond a certain distance, the expansion becomes dominant. Galaxies begin to recede at speeds that increase with distance, and eventually there are galaxies so far away that the expansion of space between us and them is faster than the speed of light. Again, not because they are moving through space that fast, but because the space itself is stretching so quickly. This leads to a very important idea. There are parts of the universe that are, in a practical sense, unreachable. Not just difficult to reach, not just far away, but fundamentally out of reach. Even if you could travel at the speed of light, even if you started right now and continued forever, you would never arrive. Because the distance between you and those regions is increasing faster than you can close it. So in those cases, the journey doesn't just take a very long time, it never completes. Now let's bring that back to the idea of crossing the universe. If the universe were static, if distances stayed fixed, then crossing it would simply be a matter of time and speed. It might take billions of years, but the path would be there, waiting to be traversed. But because the universe is expanding, and because that expansion accelerates over time, the situation is different. Some regions remain accessible, others become less accessible over time, and some are already beyond reach. So the universe, in a sense, is dividing itself into regions based on what can and cannot be connected. Now imagine setting out on a journey toward a very distant galaxy. At the moment you begin, that galaxy might still be within reach. Its distance is large, but not so large that expansion completely dominates, so you begin travelling. At first, you make progress. The distance decreases, slowly but steadily. But at the same time, the universe continues to expand. So the rate at which you close the gap is affected by how fast space is stretching. If your speed is high enough, you can still reach the galaxy, but if it's not, there may come a point where the expansion balances your progress. You're moving forward, but the distance isn't shrinking anymore. And beyond that point, the distance could begin to increase again. So you might find yourself in a situation where you are travelling continuously, but the destination is not getting any closer. It's not that you've stopped, it's that the universe has changed the rules of the journey. Now this doesn't happen at all distances. For nearby objects, you can still reach them in principle. But as you look farther out, more and more regions fall into this category where arrival becomes impossible, and that leads to a quiet but important realization. Crossing the entire universe, in the sense of travelling from one extreme edge to the other, may not be a meaningful concept. not because the universe is too large, but because parts of it are not connected in a way that allows for such a journey. The universe is not a single, unified space that can be traversed completely. It's a dynamic structure where connectivity depends on distance, expansion, and time. Now there's another layer to this. The expansion of the universe is not just continuing, it's accelerating. This means that over time, more and more regions will move beyond the reach of any possible traveller. Galaxies that are currently visible may eventually become unreachable, and over very long timescales, the observable universe itself will shrink in terms of what can be interacted with. Distant galaxies will fade away, their light stretched and dimmed by the expansion, so even the set of places you could, in principle, travel to is changing, it's not fixed. And that adds an interesting perspective to the idea of arrival. Because if the destination itself is part of a changing universe, then arriving is not just about reaching a location, it's about reaching it at a particular time. If you arrive too late, the conditions may have changed. If you start too late, the destination may no longer be reachable. So timing becomes part of the journey, not just how long it takes, but when it happens. Now let's step back and look at the broader picture. We began with the idea of crossing the universe as a kind of ultimate journey, a path from one side to the other. But as we have explored the expansion of space, that idea has become more complex. The universe is not static. Distances are not fixed. Some regions move away faster than you can follow, and the set of reachable destinations changes over time. So the question shifts. Instead of asking, how long would it take to cross the universe, we might ask, which parts of the universe can actually be crossed? And the answer depends on the interplay between speed, distance, and expansion. Now, there's something quietly reassuring about this, even if it feels a bit limiting at first. Because it means that the universe is not just an infinite expanse waiting to be traversed. It's a structured system with regions that are connected and regions that are not. And within the connected regions, journeys are still possible, still meaningful. You can travel between stars, between galaxies within a cluster, across parts of the universe where gravity still holds things together. So while the entire universe may not be crossable in a single, complete journey, there are still vast regions that can be explored, and those regions are already more than enough to stretch our imagination. Now, as we continue, it might be worth stepping away from the physical limits for a moment, because after exploring distance, speed, time, energy, and expansion, another question begins to emerge. Not just whether we can cross the universe, but whether the idea of crossing it is the right question to begin with. What does it really mean to cross something that has no clear edge, no fixed boundary, and no single final destination? After moving through all of this, the distances, the speeds, the limits, and the shifting nature of space itself, the original question starts to feel slightly different than it did at the beginning. Not wrong, not misguided, but incomplete in a quiet way. Because asking how long it would take to cross the universe assumes something very specific. It assumes that the universe is the kind of thing that can be crossed, and that's worth pausing on. When we talk about crossing something in everyday life, we're usually referring to something with clear boundaries. A room, a city, an ocean, even a continent. There's a starting point, an end point, and a path that connects the two. Even if the journey is long, the idea itself is simple. You begin here, you end there. But the universe doesn't quite fit into that pattern. It doesn't have a clearly defined edge that you could point to and say, that's the other side. What we have instead is the observable universe, which is not a physical boundary, but a limit based on how far light has had time to travel. Beyond that, there may be more universe, quite possibly much more, maybe even infinitely more. So already, the idea of crossing the universe becomes less clear. Crossing which part? From where to where? If the universe extends beyond what we can observe, then any journey we define is based on a limited view, not the whole structure. Now, even if we focus only on the observable universe, the part we can measure, the question still carries certain assumptions. It assumes that distances are fixed, that a path exists that can be followed from one side to the other, that with enough time and speed the journey could be completed. But as we've seen, the universe doesn't behave that way. It expands, distances change, some regions move out of reach, so the path is not stable, it evolves. And that means that crossing the universe is not like crossing a field or an ocean. It's more like trying to cross something that is constantly reshaping itself as you move. Now, this doesn't make the question meaningless, but it does suggest that we might need to reinterpret it, because perhaps the question is not really about crossing the universe in a literal sense. Perhaps it's about understanding the scale, about exploring what the limits are, about asking how far we can go and what happens along the way. In that sense, the journey becomes more important than the destination. Not in a poetic way, but in a practical one. Because at these scales, the destination is not something fixed or final. It's just another point in a continuously changing system. Now, there's another way to look at this. When we imagine crossing the universe, we often picture a straight path from one side to the other. But in reality, there is no preferred direction, no central axis, no obvious across. From any point in the universe, everything else appears to be expanding away. So the idea of crossing it depends entirely on how you define your starting point and your direction, which means that across is not a universal concept, it's a perspective. Now let's bring this back to something a bit more grounded. Imagine standing in a vast desert with no landmarks. You can walk in any direction, and you'll continue moving through the desert. But there's no clear sense of crossing it unless you know where the boundaries are. If the desert extends far beyond what you can see, you might never reach an edge. The journey would continue, but the idea of completion would remain uncertain. The universe is similar, but on a much larger scale, and with the added complexity that the desert itself is expanding as you walk. Now, there's something quietly interesting about this realization. It shifts the focus. Instead of asking whether we can cross the universe, we begin to ask what it means to move through it at all. What limits that movement? What defines what is reachable? And how those limits change over time. Because even if the entire universe cannot be crossed, there are still meaningful journeys within it. Travel between planets, between stars, between galaxies within our local group. These are all real possibilities, at least in principle. And each of them carries its own scale, its own challenges, its own sense of distance and time. So rather than thinking of the universe as something to be crossed in its entirety, it may be more useful to think of it as something to be explored in layers, each layer with its own boundaries, each layer expanding our understanding of what is possible. Now there's one more subtle point here. The question itself, how long would it take to cross the universe, invites us to think in terms of time. But as we've seen, time is not absolute. It depends on motion. It depends on perspective. So even the idea of a single answer becomes difficult. From one point of view, the journey might take billions of years. From another, it might feel much shorter. And in some cases, it might not be possible at all. So the question doesn't have a single fixed answer. It has a range of answers depending on how you approach it. And that's part of what makes it interesting. Now, stepping back from all of this, the question begins to feel less like a problem to be solved and more like a lens, a way of looking at the universe, a way of understanding its scale, its structure, and its limits. Because in trying to answer it, we've explored how large the universe is, how fast things can move, how time behaves at high speeds, how space itself expands, and how all of these factors interact. So even if we can't cross the universe in the way we initially imagined, the process of asking the question has taken us through many of the most important ideas in cosmology. And that in itself is a kind of journey, not through space, but through understanding. By the time we arrive here, something has shifted, almost without noticing exactly when it happened. The question we started with felt very direct, clear, even a little bold. How long would it take to cross the universe? It sounded like something that should have a number attached to it. A final answer waiting at the end. And in a way, we did find answers. Billions of years at the speed of light. Far longer with anything we can currently build. Perhaps shorter from the traveller's perspective if you move fast enough. Perhaps not possible at all for certain regions because the universe keeps expanding. All of those answers are true, and yet none of them quite feel like a complete ending. Because the question itself quietly opened into something much larger. Not just about distance, but about how distance works. Not just about time, but about how time can stretch and shift depending on how you move. Not just about travel, but about what it even means to arrive somewhere in a universe that doesn't stand still. So instead of trying to close everything neatly, it might be more helpful to slow things down again for a moment and return to something simple, you, where you are right now. Maybe you're lying down or sitting comfortably or just listening while doing something familiar. Wherever that is, it's a very small place compared to everything we've been talking about. A room, a building, a quiet corner of a planet that itself is just one point in a much larger structure. And yet, from your perspective, this place feels complete. You don't need to cross a galaxy to experience where you are. You don't need to measure billions of light years to feel distance. Everything that matters in your immediate experience fits into a much smaller scale. And that contrast is part of what makes this topic so interesting. Because the universe is both incredibly large and at the same time something we experience from a very specific, very local point of view. Now think back to the idea of a journey. In everyday life, a journey has a purpose. You go somewhere to reach a destination. There's a reason to arrive, and once you do, the journey is complete. But at the scale of the universe, that structure becomes less clear. There is no final edge waiting to be reached. No single point that marks the end of everything. Even the observable universe, the part we can see, is just a limit based on time and light, not a physical boundary. So the idea of a final destination begins to fade, and what remains is the journey itself, not in a poetic sense, but in a very practical one. Because every step outward, every increase in speed, every new way of thinking about space and time reveals something new. We learned that even our solar system is vast, that galaxies take tens of thousands of years to cross, even at light speed, that the space between galaxies stretches into millions of years, that the universe itself is expanding, changing the rules as we go. That time is not fixed, and that moving faster can change how it's experienced. That energy places limits on how far we can push our speed, and that even the idea of crossing the universe might not apply in the way we first imagined. Each of those steps didn't just bring us closer to an answer, they expanded the question, and that's something worth holding on to. Because sometimes, understanding grows not by reaching the end, but by exploring what lies along the way. Now, there's another quiet detail here. Even though the universe is vast beyond anything we can fully imagine, we don't experience it all at once. We experience it piece by piece, through light that has travelled for years, centuries, or billions of years to reach us. Through observations, measurements, and ideas that slowly build a picture over time. So in a sense, we are already part of a journey, not one where we physically cross the universe, but one where we learn about it gradually, step by step. And that journey doesn't require travelling at the speed of light. It happens here, in moments like this. Now, there's something calming about that, because it means that even though the universe is unimaginably large, you don't need to cross it to engage with it. You don't need to reach the edge or find a final destination. It's already present, in the light that reaches you, in the sky above, in the ideas that connect all of this together. So the question we started with, how long would it take to cross the universe, doesn't really end with a single number. It ends with a perspective, that the universe is not just something to be crossed, but something to be understood. And that understanding unfolds gradually, just like a journey. Now, as things settle, you might notice that the urgency of the question has faded a little. Not because it's been answered completely, but because it no longer needs a sharp conclusion. The universe doesn't rush, and neither does the process of understanding it. So instead of arriving at a final point, we simply find ourselves here, at the end of this particular path, with a slightly different view than when we began. And if you let that thought linger for a moment, there's a quiet kind of comfort in it. That not every question needs a final answer. That sometimes the act of exploring is enough. And that even in a universe this large, there's still room for slow thinking, for gentle curiosity, and for simply letting ideas settle, one after another, without needing to rush toward an end. So as you stay here, wherever you are, you might just let all of this drift softly into the background. The distances, the galaxies, the expansion of space, all of it continuing quietly, far beyond immediate reach. And here, much closer, things remain simple, a moment, a breath. And the sense that even without crossing the universe, you've still travelled quite a long way.